If humanity were to vanish tomorrow, how long would our cities, machines, and knowledge survive? 1,000 years? 1,000,000? Now imagine trying to find evidence of a civilization that disappeared not a few centuries ago, but hundreds of millions of years in the past. Would anything be left at all? Would we even know where to look? In 2018, two NASA-affiliated scientists posed a radical question. Could we be the first industrial civilization on Earth, or just the latest? Earth is a restless planet. Oceans rise, continents move, and time erases nearly everything. Let's explore that unsettling possibility. What signs a long-lost civilization might leave behind, why we may have already missed them, and what it means for our future and the search for life beyond Earth. The thought experiment that sparked a scientific question. In 2018, two scientists, Gavin Schmidt, a climate scientist at NASA, and Adam Frank, an astrophysicist from the University of Rochester, posed a question. They called it the Silurian hypothesis, named after a fictional ancient reptilian species from the British television show Doctor Who. The name was playful, but the question was serious. If an advanced civilization had lived on Earth millions of years before humans, would we even know? Would we be able to find any trace of it today? Or would time, geology, and nature have erased all the evidence? This wasn't about lost cities under the sea or aliens visiting in ancient times. It was a scientific look at the limits of the geologic record, the layers of rock and sediment that hold the story of Earth's past. The Silurian hypothesis was a way of testing how well science can detect signs of technology in Earth's deep history. To understand the scale of the question, it helps to consider just how old the Earth is. Our planet is about 4.5 billion years old. Complex life, like animals with bones or shells, has only been around for about 540 million years. Human civilization, the kind that builds cities, writes books, and sends satellites into orbit, has only existed for around 10,000 years. That's less than a blink on the geologic timescale. So what if something like us had lived on Earth long before the age of mammals? What if they rose, thrived, built things, and then disappeared completely, millions of years before humans appeared? Schmidt and Frank looked at what a truly industrial civilization might leave behind. They weren't looking for bones or stone tools. They were looking for signals, chemical or environmental markers that a civilization might leave behind without meaning to. For example, humans today are changing the atmosphere by burning fossil fuels. We're leaving behind plastics in the oceans, radioactive waste in the ground, and unusual spikes of carbon in the air. If someone looked at Earth's rocks millions of years in the future, would they be able to detect this human activity, even if all our buildings and artifacts were long gone? They found that the answer is not simple. The Earth is constantly changing. Plate tectonics moves continents. Wind and water wear down mountains. Volcanoes and oceans bury, melt, and crush what lies beneath. Over millions of years, almost everything disappears. Take cities, for example. Most are built near coastlines or rivers, places that are geologically unstable. Over tens of thousands of years, many would be underwater. Over millions of years, they would likely be erased by erosion or buried under layers of sediment. Even large structures like skyscrapers wouldn't last forever. Steel rusts, concrete crumbles, glass breaks down. In time, they would all vanish. Fossilization is rare. It needs the right conditions: quick burial, low oxygen, and mineral-rich waters. Most life that dies does not fossilize. So if an intelligent species existed in the distant past, but was small in number or limited in range, it might leave no fossils at all. Instead of bones or buildings, Schmidt and Frank looked at what scientists call anthropogenic markers, traces left behind by modern human activity. They studied what we are currently putting into the environment, things like industrial chemicals, plastic pollution, and carbon isotopes from burning fossil fuels. These signals could be preserved in sediments and ice cores. In theory, similar markers could exist in ancient layers of rock. So the Silurian hypothesis became a way of exploring those ancient layers with new eyes. Could there be odd chemical signals in the rock record that don't match natural processes? Could there be spikes in carbon or heavy metals from some past event that wasn't volcanic or caused by a known extinction? And if there were, would we even recognize it for what it was? If we only look for fossils or artifacts, we might miss something. But if we learn to read the chemistry of the Earth's layers more carefully, we might start to see patterns we hadn't noticed before. That also brings up another interesting question. If signs of a civilization are so easy to lose, what does that say about our own? Will the future remember us? 1,000,000 years from now, will any trace of humans remain? Will we leave behind a clear signal that someone or something could detect? Or will we disappear into the Earth's memory just like any other species? Human history is short, and the planet's history is extremely long. We tend to think of the Earth as something we can understand, but we've only scratched the surface, literally. The rocks beneath our feet have stories we may never fully read. Why the geologic record might hide civilizations. When scientists study the past, they often rely on the geologic record, the layers of rock, soil, and sediment that have built up over time. These layers are like a diary of the Earth. They hold signs of ancient life, past climates, and massive events like asteroid impacts or volcanic eruptions. But that diary isn't complete. Much of it has been smudged, torn, or rewritten by the planet itself. One of the biggest forces at work is erosion. Rain, wind, rivers, and waves constantly wear down the surface of the planet. Over time, even the strongest materials can be broken apart. Mountains are slowly ground down into dust. Valleys fill with mud and sand. If an ancient city was once built in a region where rain and rivers are strong, that city could be worn away until not a single block remains. Then there's the movement of continents. The Earth's surface is made up of large plates that float on top of the hot, flowing rock beneath. These plates shift and slide, sometimes crashing into each other, sometimes pulling apart. This is the force behind earthquakes and the rise of mountain ranges. It also means that over millions of years, land can disappear into the deep earth. A city built on a continent's edge could be pushed beneath another plate and melted into magma. The process is called subduction. It's slow, but it's relentless. Whole sections of Earth's surface vanish in this way, taking everything with them. Volcanoes are another way the planet erases itself. When a volcano erupts, it can cover the ground with ash and lava. That might seem like a way to preserve something, like a time capsule. But more often, it destroys. Heat melts, ash buries, and gases change the chemistry of the air and soil. A powerful eruption can wipe out anything built nearby. And over time, the land reshapes itself around these eruptions. What once was a plain might become a mountain. What once was a lake might become a desert. The clues are lost in the transformation. Glaciers play a similar role. During ice ages, thick sheets of ice cover large parts of the planet. These glaciers are heavy and slow, but they scrape across the land like sandpaper. They grind down hills, crush forests, and move rocks the size of houses. Anything in their path, buildings, roads, even entire cities, would be broken and carried away. And when the ice melts, it leaves behind a landscape that looks nothing like what came before. Even without these dramatic forces, time alone is enough to erase evidence. Most materials break down over long periods. Wood rots, metal rusts. Plastics can last longer, but even they begin to crumble and fall apart after centuries or millennia. If a civilization existed 50 million years ago, what would be left of it now? Even strong structures like dams or tunnels might not survive. And the deeper you go into the past, the fewer chances there are for anything to remain. Fossils give us some idea of how rare preservation really is. Most living things never become fossils. Soft tissues almost never survive. And when fossils do form, they can still be crushed, weathered, or destroyed by the same forces that shape the land. This rarity becomes important when thinking about intelligent life. Humans today are spread across the globe, but most of our population lives in cities and towns that cover a small fraction of the Earth's surface. If a past civilization had a similar distribution, just a few large centers with most people living in a few regions, there's a chance that very little of it would end up preserved. If it lasted only a few thousand years, as human civilization has so far, the window for preservation would be even smaller. Some scientists have pointed out that there are gaps in the geologic record. These are called unconformities. In some areas, millions of years of rock layers are missing. They were either never deposited or were eroded away before new layers formed. In these blank spots, anything that might have been left behind is now gone. We have found signs of mass extinctions, giant impacts, and ancient climate shifts. But we've also seen how fragile those signs are. A few inches of missing rock could mean missing millions of years of history. There's also the question of how much we even know about the rock record we have. Most geological studies focus on certain time periods or areas. The ocean floor, for example, is largely unexplored. Yet it covers more than 70% of the planet. Most of the ocean crust is younger than 200 million years because older seafloor gets recycled back into the Earth. That means any signs of an older civilization, if it had been based on island chains or coastal areas, would be gone along with that crust. Even on land, many places are hard to study. Thick forests, deserts, and mountain ranges make it difficult to find and explore buried layers. Much of the rock we can reach has already been altered by heat, pressure, or chemical changes. The clues are faint, and they get fainter the deeper we look. Still, some signs might survive, at least in theory. Chemical fingerprints, like sudden shifts in carbon levels or strange concentrations of metals, can last longer than physical structures. These are the kinds of things scientists look for when they study mass extinctions or global climate changes in the past. But even these signals can be hard to read. Nature creates its own strange patterns. A volcanic eruption can cause a spike in carbon dioxide. A meteor strike can scatter rare metals. How do we tell the difference between a natural event and an artificial one? The Earth is a restless planet. It keeps few secrets for long, and even fewer forever. Time crushes everything eventually. In a world like this, it's not hard to imagine that something could rise to greatness, vanish completely, and leave behind no clear trace. The silence doesn't tell us as much as we might think. In the end, the absence of evidence may simply mean the evidence is lost, buried not by conspiracy, but by the slow grinding forces of the Earth itself. The illusion of uniqueness. Most people don't question whether human civilization is the first. It's just something we assume. We look around at what we've built, cities, satellites, power plants, and think this must be the peak of evolution. We think we are unique, not just in the world today, but in all of Earth's long story. But when you really stop and look at the scale of time, that belief becomes harder to hold on to. Human civilization is incredibly young. Modern humans, Homo sapiens, have been around for about 300,000 years. But the kind of complex society we live in, agriculture, writing, buildings, machines, only began about 10,000 years ago. That's less than 0.0003% of Earth's total history. If the history of Earth was stretched across a full 24-hour day, human civilization would appear only in the last few seconds before midnight. Everything we've built would be just a blink. Before us came dinosaurs, which lived for over 160 million years. Before them, giant sea creatures ruled the oceans. Before that, there were forests filled with insects the size of birds, and even earlier, single-celled life that lived quietly for billions of years. Life on Earth has taken many strange forms, and it has gone through many waves of creation and destruction. Entire branches of life have risen, thrived, and vanished, leaving only tiny traces behind. So why do we assume that intelligence, the kind that builds machines and changes the planet, only happened once? Why do we believe we are the only species to reach this level of development? Part of the answer may lie in emotion, not science. We like to feel special. It's comforting to believe we are the first and only to shape the world in this way. It gives our lives a sense of purpose. It supports the idea that history was always leading to us, that we are the final product of nature's long experiment. But nature doesn't work that way. Evolution is not a straight path. It's full of dead ends, strange turns, and repeat patterns. In fact, intelligence itself has evolved more than once. Birds, dolphins, octopuses, and some primates have all shown signs of advanced thinking. Some use tools, some understand language, some can solve puzzles or recognize themselves in mirrors. These are not just tricks. They are signs of real cognitive depth. In some cases, these animals live in social groups, pass down learned behaviors, and adapt to new situations with surprising creativity. But none of them have reached the point of industrial civilization. None have built machines or changed the atmosphere. Why? Maybe they didn't need to. Maybe intelligence doesn't always lead to technology. Or maybe they simply haven't had enough time. If something had happened to wipe out humans 5,000 years ago, there would have been no trace of cities, no history books, no evidence we were ever here. The rise of technology is fast, but it's also fragile. If intelligence can evolve more than once, then maybe civilization can too. Maybe it already has. There's another part of the problem. Our science is shaped by what we expect to find. If we believe that humans are the only technological species in Earth's history, then we don't look for signs of others. We see unusual chemical changes in rock layers and explain them as natural events: volcanoes, climate shifts, asteroid strikes. We don't ask if they could be something else. And when we do find strange patterns, we rarely think of civilization as a cause. It's just not part of the scientific framework. This bias is understandable. Science tries to avoid jumping to conclusions. Extraordinary claims require extraordinary evidence. If someone said they had proof of an ancient civilization from 100 million years ago, most scientists would demand very strong support. That's the way it should be. But at the same time, it means we may miss signs that are already in front of us, because we aren't trained to see them. There are a few examples where strange signals in the geologic record have sparked questions. In some layers of rock, scientists have found odd spikes in carbon, metals, or radioactive elements. These are usually explained by natural causes. But what if, just once, one of these events was caused by something else? What if a past civilization used fossil fuels, just like we do, and left behind a carbon spike? What if it triggered climate change, or even its own extinction? We don't know the answers, but asking the question doesn't hurt. In fact, it opens up new ways to think about our own future. If civilizations can rise and fall and leave almost nothing behind, what will remain of our time millions of years from now? Will the Earth remember us at all? Intelligence and civilization might be more like a pattern than an accident. Given enough time, life may keep experimenting with complexity. It may build minds again and again in different forms on different branches of the tree of life. Some of those minds might build cities, some might build machines, some might collapse before they ever get the chance. This doesn't mean there were cities in the time of dinosaurs, or that machines once roamed ancient forests, but it means we should stay open to the possibility. Earth's deep history is full of surprises. New fossils are found every year, new tools, new species, new mysteries. And with every discovery, our understanding of the past changes. What we thought was certain yesterday becomes questionable today. Believing we are the first is not a scientific truth. It's a story we tell ourselves. And like all stories, it can change. Decoding Deep Time: How We Study Earth's Distant Past. Each layer or stratum of rock holds part of Earth's story. The deeper the layer, the older it is, at least in places where the ground hasn't been broken up or flipped by earthquakes or mountain building. Geologists begin by looking at the shape and content of these rock layers. Different environments, rivers, oceans, deserts, volcanic plains, leave behind different types of rock. Sandstone might form where there were ancient beaches or deserts. Shale often forms from mud at the bottom of lakes or seas. Limestone is often built from the shells of tiny sea creatures. By studying the minerals in these rocks and how they're arranged, scientists can figure out what kind of place that layer came from and what the climate might have been like. Rocks don't just tell us where we were, they can also show us when. This is where fossils come in. Sometimes it's a full skeleton, other times it's just a shell, a tooth, or even a footprint pressed into mud that turned to stone. Fossils help place rock layers in time because different species lived during different periods. If a layer has a fossil from a creature known to live 100 million years ago, then that layer is likely from that same time. Sometimes the fossils are tiny, smaller than a grain of sand. These are called microfossils. Even though they're small, they're just as useful. Many of them come from single-celled organisms that lived in the sea. These creatures changed quickly over time, so their fossils are good time markers. Microfossils are found all over the world, which helps scientists link distant rock layers to each other. But there's more to a rock than just what we can see with our eyes. Inside the minerals and the fossils are chemical signatures. These are traces of elements and isotopes that formed under very specific conditions. For example, the ratio of certain carbon isotopes can tell scientists about how much life was on Earth at a given time. A sudden drop in carbon-13, for instance, might mean a mass extinction event occurred, something that wiped out large amounts of plant or animal life. Other elements, like iridium, can point to events from space. Iridium is rare in Earth's crust, but common in asteroids. A sharp spike in iridium in a rock layer suggests that an asteroid hit the planet at that time. This is how scientists first confirmed the theory that a giant asteroid impact helped wipe out the dinosaurs 66 million years ago. The evidence wasn't a crater at first. It was a thin layer of clay spread across the globe containing unusual amounts of iridium. Some rocks carry signs of climate too. The presence of certain oxygen isotopes in the shells of ancient sea creatures can reveal the temperature of the oceans at the time they lived. Layers of ash can show when volcanoes erupted. Layers of salt or dried mud might point to ancient droughts or evaporated lakes. Even tiny bubbles of air trapped in ice cores from glaciers can hold a snapshot of Earth's ancient atmosphere, though those only go back about 800,000 years. These methods help build a timeline. Scientists use radiometric dating to measure how much of certain radioactive elements are left in rocks. These elements decay at a known rate, like a ticking clock. Uranium, for example, slowly turns into lead over billions of years. By comparing how much uranium is left and how much lead has formed, scientists can estimate the rock's age. Different elements are used for different time ranges. Carbon, 14 for recent remains, potassium argon for older volcanic rocks, and uranium lead for some of the oldest materials on Earth. Putting all this together, fossils, rock types, chemical data, and radiometric dates, scientists can piece together a picture of Earth's past. They can see when continents moved, when oceans rose and fell, when mountains formed and were worn down again. They can track the rise and fall of species, the spread of forests and deserts, the changing of climates. But it's not always easy to interpret what the picture means. When something unusual appears in the record, a sudden change in temperature, a spike in carbon, a drop in oxygen, a strange metal, it raises questions. What caused it? Was it a natural event, a volcano, an asteroid, or something else? A spike in carbon could be from burning fossil fuels. A layer of plastics could last millions of years if the conditions are right. A sudden rise in heavy metals might not come from a volcano, but from widespread mining and industry. But finding that kind of evidence is extremely hard. Human activity today leaves behind chemical signatures, pesticides, industrial waste, synthetic materials that are new to the planet. Some of these might survive deep time, but most will not. The same would be true for any past civilization. Their signals would have to be large enough, strange enough, and different enough from natural processes to be noticed. The deeper into time we go, the less we can be sure. Rocks don't lie, but they don't explain themselves either. They offer hints, not answers. And the farther back we look, the more those hints begin to blur. That's why Earth's history is still full of mystery. For all we know, for all we've learned, there's still so much we don't understand. New tools, like satellite imaging, deep ocean drilling, and advanced chemical analysis, are helping us see things we never could before. Scientists can now examine tiny chemical traces with incredible detail, or search through sediments for ancient DNA. But even with these advances, the past remains stubborn. It reveals itself slowly, in pieces. The geological record's memory loss. Over time, wind, water, and ice grind down the surface of the Earth. Glaciers scrape across land. Rain eats away at mountains, carrying bits of rock downstream to be dropped elsewhere. In places where rock is worn away instead of built up, no new layers can form. Instead of preserving time, these places lose it. The history that was once written there is carried away piece by piece until nothing is left. Mountains rise, valleys sink, and rock layers are bent or snapped like cards in a stack. Sometimes the rocks are pushed deep into the earth. Minerals change. Solid stone becomes something else. A whole layer may melt or recrystallize until it no longer holds any sign of the life or climate it once recorded. This reshaping of the Earth can erase hundreds of millions of years. And because this process happens again and again over time, it leaves behind a record that's far from perfect. Sedimentation, the process that creates new layers, doesn't happen everywhere. It tends to occur in low places like river deltas, lakes, or ocean floors. These are spots where mud, sand, and silt settle and build up over time. Uplands, hilltops, and dry plains, on the other hand, may go millions of years without gaining a single new layer. That means large parts of the Earth's surface are blank. This unconformity can mean that there are places where two rock layers are separated by a gap that might represent millions or even hundreds of millions of years. In some spots, a single inch of rock might jump from one era to another with nothing in between. The cause could be erosion, or a long pause in deposition, or both. Some unconformities are dramatic. In the Grand Canyon, there's a well-known example where ancient rock, more than 1 billion years old, sits directly beneath a much younger layer, hundreds of millions of years newer. In between, a massive stretch of history is gone. What happened during that time? What life may have existed? What climates, landscapes, or even civilizations might have come and gone? Even when rocks and fossils are preserved, they may not tell the whole story. Most organisms do not fossilize. Soft-bodied animals, like jellyfish or worms, almost never become fossils. Neither do most plants. This means that what we know about the past comes from a small sample. It's like trying to understand an entire novel by reading a few torn pages from each chapter. We see pieces of ancient life, but not the full picture. We may miss key events or entire ecosystems. There could be long periods in Earth's history where life thrived, changed, and vanished, leaving little or no trace. That's why some scientists call the geologic record a biased archive. It preserves some things better than others. It favors environments where sediment builds up, like the ocean floor. It favors hard parts, bones, shells, and teeth, over soft tissue. It favors species that were widespread and long-lasting. And it favors time periods when the conditions for fossilization were just right. For a civilization, this bias would be especially harsh. Civilizations often live in areas that are more likely to be disturbed or destroyed over time. And many signs of a civilization, tools, buildings, even cities, can disappear completely if not buried and preserved quickly. Why we don't know what was here before dinosaurs. When people think of ancient Earth, they often picture dinosaurs roaming through forests or towering over swamps. But even dinosaurs are fairly recent in Earth's timeline. They first appeared about 240 million years ago during the Triassic period. Before that, the planet had already lived through more than 4 billion years of history. Most of that time is a mystery to us. Rocks that are older than 250 million years exist, but they're rare and often damaged. These ancient rocks are harder to find, harder to study, and harder to read. They've been changed by pressure, heat, and time. They've been pushed deep into the Earth and brought back again. They've been melted, cracked, or erased. What survives from that far back is only a small sample, scattered across the world like crumbs from a forgotten meal. This means we have very little direct knowledge about what life was like before the age of dinosaurs. We do know some things. Scientists have found fossils of early fish, simple plants, and soft-bodied animals that lived more than 500 million years ago. They've studied the strange forms of life that came before the Cambrian explosion, around 541 million years ago, when complex animals suddenly became much more common. But the farther back you go, the harder it gets. The evidence becomes faint. Sometimes it's just tiny marks in rock, or chemical traces left by single-celled organisms. For anything like a civilization, something large, organized, and possibly technological, the lack of evidence becomes a much bigger problem. A civilization that existed 300 or 400 million years ago would have had to leave behind something truly massive to be noticed now. Even then, the odds are against it. Most of the ocean floor, for example, is younger than 200 million years. Older oceanic crust has already been pulled back into the Earth and replaced. So if anything once existed on or near those ancient ocean floors, it's gone now. Even on land, many rocks older than 250 million years have been transformed. Heat and pressure deep underground can turn sedimentary rock into metamorphic rock. There are some places where older rocks remain. In parts of Canada, Australia, and Africa, geologists have found pieces of crust that date back over 3 billion years. These regions are known as cratons, stable parts of the Earth's surface that haven't moved much in a very long time. But these ancient rocks are often worn down to their base. They don't have the layered structure that comes from steady sedimentation. They don't hold many fossils, and when they do, it's usually the simple kinds: microscopic life, algae mats, or chemical residues. That leaves us with a problem. If anything like an intelligent civilization existed before the age of dinosaurs, the record we would need to confirm it has mostly been destroyed or changed. The buildings, tools, or other artifacts such a civilization might leave behind are unlikely to survive deep time. Most would be made of materials that rot, rust, or decay. Even if something did survive, like a metal object buried in sediment, chances are it would be gone by now. Oxidation, corrosion, and geological processes would break it down long before we could find it. Even large-scale effects might be erased. Some plastics might survive in deep-sea sediments. Some carbon changes might stay in the atmosphere or in the rock layers. But over hundreds of millions of years, most of that would fade. The deeper in time you go, the less even major changes stand out. This is especially true in periods where rocks are missing entirely. Across much of the world, there are long stretches where no rocks older than a certain age exist. These gaps make it hard to build a clear picture of what the planet was like. The time before dinosaurs includes several mass extinctions and strange shifts in life and climate. But even those events, dramatic as they were, are sometimes hard to study. The evidence is thin. Some extinction events are known mostly from small changes in fossil types or slight shifts in chemical layers. If something as massive as a global extinction can leave such a faint mark, it's easy to imagine that a smaller event, like the rise and fall of a civilization, could vanish completely. Even the tools we use to study deep time have limits. Radiometric dating can give us ages for rocks, but only if the right minerals are present. Fossils can tell us about life, but only if life was preserved, and most life isn't. Chemical markers can hint at changes in the environment, but they can be hard to interpret. Without context, it's just a line on a graph. The lack of evidence doesn't prove something didn't happen. It only shows that we don't have the right pieces to say for sure. When you're dealing with timescales that stretch across hundreds of millions of years, silence is common. Earth's memory gets worse the deeper you go. How mass extinctions reboot the planet's surface. Every so often, something happens on Earth that doesn't just change the planet, it resets it. These are the mass extinctions, moments when most life disappears in a geological instant. There have been at least 5 of them in the last 500 million years, and each time, the effects were more than just biological. These events didn't just wipe out species, they also reshaped the Earth's surface. Landscapes changed, climates shifted, oceans turned over. When we hear the word extinction, we often think of animals dying off, like the dinosaurs. But a mass extinction is much bigger than that. It's a global event. It leaves scars across the planet, both above ground and below. For a short time, geologically speaking, the rules of life are suspended. Forests vanish, coral reefs collapse, food chains break, and while nature eventually recovers, it comes back changed. The world that grows back is not the same as the one that was lost. These events are important for anyone thinking about the distant past. If a civilization existed long before humans, whether it was animal, plant-based, or something else entirely, it might have been wiped away in one of these great resets. One of the most famous mass extinctions happened 66 million years ago, at the end of the Cretaceous period. It's known for killing off the dinosaurs, but the damage went far beyond that. Scientists believe a large asteroid, around 10 kilometers wide, struck near what is now the Yucatan Peninsula in Mexico. The impact released more energy than 1 billion nuclear bombs. It created a crater over 180 kilometers wide and sent a shockwave through the planet. The debris thrown into the sky blocked out sunlight for months, maybe years. Temperatures dropped, plants died, animals starved, wildfires swept across entire continents. In the oceans, plankton collapsed and the food web beneath the waves broke apart. Over 75% of all species disappeared in a relatively short amount of time. Massive earthquakes and tsunamis reshaped the land. Ash and debris rained down, covering everything in a layer of dust and soot that later hardened into rock. That layer, known as the Cretaceous-Paleogene boundary, is found all over the world. It's one of the few moments in deep time where something truly global was recorded in stone. Anything on the surface, in the impact zone, or even far away, might be destroyed or buried under layers of new material. Forests turned to ash. Cities, if any existed, would crumble or burn. Artifacts made of wood, cloth, or even metal wouldn't last long. The chemical traces of pollution or agriculture could be overwhelmed by the fallout. In some places, new rock layers would form so quickly that nothing underneath them could be found again. Volcanoes can do something similar. Around 252 million years ago, the largest extinction in Earth's history took place, the Permian-Triassic extinction, often called the Great Dying. During this event, more than 90% of marine species and 70% of land species vanished. Scientists believe that one of the main causes was a series of massive volcanic eruptions in what is now Siberia. These eruptions didn't last for days or weeks. They went on for hundreds of thousands of years. They poured out lava over an area bigger than the continental United States. They filled the atmosphere with greenhouse gases, sulfur, and ash. Temperatures soared. Oceans became acidic and lost their oxygen. Life struggled to survive. Just like the asteroid strike, the Siberian traps, named for the step-like layers of rock they created, changed the land in ways that go far beyond the loss of life. The heat and pressure of the lava baked the rocks below. Ash buried entire regions. Chemical reactions altered the soil and water. For any trace of a civilization in that area, the chance of survival would have been almost zero. The surface was reset, and anything left behind was either incinerated or entombed. These are not the only mass extinctions. There was one about 443 million years ago during the Ordovician period, likely caused by a sudden cooling of the planet. Another took place 374 million years ago in the Devonian, possibly linked to changes in sea level and oxygen levels in the oceans. Each time, the result was the same. Ecosystems collapsed, life was pushed back to its roots, and new layers of rock covered what came before. Some of these extinction events left very clear layers in the geological record. Others did not. In many cases, the events that caused them, asteroids, volcanoes, climate shifts, also disrupted sedimentation. Instead of smooth, readable layers, you get breaks, gaps, or mixed-up sediments. If a civilization rose and fell just before or during a mass extinction, its signal might be completely erased. Not just biologically, but geologically. Mass extinctions open space for new life. After each major die-off, evolution starts to fill the gaps. New species appear, old ones vanish, forests regrow, coral reefs reassemble, the Earth becomes something new. In the long run, the old world is forgotten, not just by us, but by the planet itself. There was one about 443 million years ago during the Ordovician period, likely caused by a sudden cooling of the planet. Years old. Much of the land we walk on today is much newer. It has been remade again and again by fire, water, and time. Each mass extinction is like a giant hand sweeping across the chalkboard, wiping away everything that came before. Industrial fingerprints in the rock record. Imagine a future geologist looking back at our time millions of years from now. What would they find? The answer depends on what kind of traces we are leaving behind. Our industrial civilization is changing the Earth in many ways, through building, digging, burning, and manufacturing. And some of these changes don't blend in with the normal flow of Earth's cycles. These are the marks of industry, and they may last longer than anything else we leave behind. Plastics are everywhere, in oceans, soil, and even in the air. Unlike wood or cloth, plastics don't break down easily. Some types might last for thousands or even millions of years under the right conditions. Bits of plastic might end up trapped in sediments, buried under sand or silt, and eventually turned into part of the rock record. Scientists already find microplastics in remote parts of the world, on mountain peaks, deep under the sea, and inside ice cores. These small fragments are spreading so widely that they could form a future marker layer, something that geologists can point to as a sign of our time. There are also chemicals we make that don't occur in nature. These include pesticides, fire retardants, industrial coolants, and pharmaceutical waste. Some of these chemicals are very stable. Once released, they don't easily go away. They may be absorbed into the ground, carried into rivers and oceans, and eventually become part of sediment layers. Even if the chemical itself breaks down, it can leave behind a signature, something that shows it was once there. Another marker is the presence of certain isotopes. These are versions of elements with different numbers of neutrons. Some isotopes are stable, but others are radioactive, meaning they break down over time. Our use of nuclear power and weapons has released artificial isotopes into the environment. Strontium-90, cesium-137, plutonium-239. These did not exist in the natural environment before the 20th century. They now appear in soil and sediment layers around the world, especially in places that saw nuclear testing. Because some of these isotopes decay very slowly, they could be detected for thousands or millions of years. A sharp rise in their presence would be a clear sign of an industrial civilization. We've also changed the ratios of naturally occurring isotopes. Burning fossil fuels, for example, changes the balance of carbon isotopes in the atmosphere and in organic matter. Trees, ocean life, and even cave deposits absorb this altered carbon. When geologists look at layers of limestone or coal in the future, they might notice that something unusual happened around the time we were burning so much oil, coal, and gas. That shift could stand out as a strange blip in the carbon cycle. Mining is another major activity that leaves a trace. When we dig for metals, we don't just move the surface, we often dig deep. We separate valuable materials from the surrounding rock and pile the leftovers, called tailings, in waste heaps. These tailings can contain unusual concentrations of heavy metals like lead, cadmium, arsenic, and mercury. If buried and preserved, these concentrated zones might still be visible in the rock record of the future. They might look like thin, unnatural stripes of metal-rich sediment. In places where mining was especially intense, the signature might be unmistakable. Urban areas could also leave behind strange geological features. Concrete, asphalt, and steel do not occur in nature in their manufactured form. Over time, these materials break down, but under the right conditions, they could fossilize. Buried cities might compress into odd layers of artificial rock, filled with sharp angles, glass, metal fragments, and plastic bits. Some researchers call this type of new material technofossils, objects that were clearly made by technology and then ended up buried in the earth. The construction of roads, dams, and large buildings also changes the physical shape of the landscape. We flatten hills, divert rivers, and cut into rock. Even if our structures don't survive, the altered landforms might. A sharp edge where a quarry once stood, a perfectly flat area where a city was built. A series of regular shapes in the subsoil that don't match natural patterns. These shapes might last long after the materials themselves have vanished. Even our farming methods might leave a lasting mark. The way we've cleared forests, plowed land, and used fertilizers has changed the chemistry of soils. In some areas, the top layer of Earth is now thinner or more eroded than it was in the past. In others, artificial nitrogen has built up in ways that don't match the natural nitrogen cycle. These changes may be recorded in future soils, especially if they are buried under new layers of sediment. Taken together, these signals form a kind of fingerprint. Scientists call this possible future layer the Anthropocene, meaning the age of humans. It would be a narrow band in the geological record, but it might stand out sharply from what came before. If our civilization were to collapse today, what would survive? Skyscrapers and satellites would fall. Roads would crack and crumble. Forests and animals would slowly return. But underground, some of our fingerprints might still remain. In lake beds, river deltas, and ocean floors, places where sediments build up, the traces of our time could be pressed into stone. If another species dug them up millions of years from now, they might puzzle over the odd combination of synthetic materials and altered chemistry. That's why our own fingerprint matters. By studying the kinds of signals we are leaving behind, we get a better idea of what to look for in the deep past. If plastics can survive, we might look for plastic-like compounds in older rocks. If isotopes can mark our time, we might search for similar blips in the record elsewhere. If mining leaves chemical scars, we might check for metal concentrations that don't fit natural processes. So far, no one has found anything in ancient rocks that definitively points to a lost civilization. But that doesn't mean it couldn't have happened. It just means the evidence, if it exists, has either not been found or has already been erased. The more we understand our own footprint, the better we can search for others. How would future geologists recognize the Anthropocene? Let's imagine it's 100 million years from now. The continents have shifted, new oceans have opened, and old ones have closed. Entire mountain ranges have risen and eroded. A new civilization, whether from Earth or somewhere else, begins to study the rocks left behind by time. They dig into the layers, peeling back the story of the planet one band of stone at a time. At some point, they come across something odd. They've reached the Anthropocene. Some say the Anthropocene started during the Industrial Revolution, when coal and steam transformed the world. Others trace it back to the middle of the 20th century, when nuclear weapons, plastics, and large-scale farming left unmistakable marks across the planet. But the real question is, will anything from our time survive long enough to be seen millions of years from now? In the right conditions, buried in mud, away from sunlight and oxygen, some plastics might last for millions of years. They might be broken down into microplastics, but those tiny pieces could still be trapped in rock layers, fused into sediment, or even preserved as fossils of a sort. Future scientists might find odd fragments that don't match any natural compound. They'd be lightweight, colorful, and filled with strange chemical bonds. Even if they've broken down, the chemical traces might remain. Concrete is one of the most used materials on Earth today. It's found in buildings, roads, bridges, and dams. Over time, it cracks and weathers, but in some places, chunks of concrete might get buried and fossilized. Future geologists could find unnatural mixtures of lime, sand, and gravel, hardened into unusual textures not seen in natural rocks. These may even show rebar or metal structures inside, which would seem even more unnatural. If mining waste gets buried or washed into lakes, they could form dark metallic bands in sediment layers. Future scientists might drill a core sample and suddenly find a spike in strange metal ratios, too high to be natural and too uniform to be from volcanoes or meteorites. changes in biology might also stand out. Our time has seen a rapid loss of species. Some call it the sixth mass extinction. At the same time, we've spread certain animals and plants all over the world. Rats, pigeons, domestic dogs and cats, corn, wheat, soybeans. If any of these species leave behind fossil remains in great numbers and across many regions, they might appear as a strange pattern, a sudden worldwide spread of a few select organisms. This kind of rapid and global shift in biology is rare in the fossil record. Industrial civilizations often discharge waste into the sea, both chemical and physical. Fertilizer runoff from farming can create dead zones, places where oxygen levels drop so low that most life dies off. These events leave marks in the sea floor. Layers of dark, organic-rich mud form in places where they normally wouldn't. If another species, millions of years from now, looked at a sediment core from that time, they might wonder why so much carbon collected all at once, or why certain species disappeared in that layer while others appeared in large numbers. Even pollen grains might tell a story. The rise of agriculture and tree clearing has changed the types of plants growing on large areas of land. Layers of lakebed mud and peat bogs can trap pollen for thousands of years. By studying these, scientists can see the moment when forests gave way to farms and grasslands, when native plants were replaced by crops and weeds. This change is sharp and sudden in many areas, and might still be visible far into the future. But for all these signals to be readable, they have to survive deep time. There are some places where time moves more slowly, ocean sediments that lie quiet and undisturbed, caves that slowly build layers of mineral crust, deep lakes that collect yearly bands of silt and dust. In these special spots, the signs of our world might be held like pages in a book. If future scientists find those pages, they'll read about us, not through our buildings or machines, but through the traces we never meant to leave behind. The carbon in our breath, the chemicals in our rivers, the plastics in our oceans, the radioactivity in our skies. They won't see our faces, but they'll know that something strange happened. It will be up to them to decide what it all meant, whether it was the rise of something new or the end of something brief. The Great Decay: Why Advanced Tech Doesn't Last. Walk through any city and you'll see things that look solid. Steel towers rising into the sky, concrete bridges stretching across rivers, cars, roads, machines, lights. It all seems so strong, so permanent. But if you step away from the noise and the people, if you leave these things alone for long enough, they begin to fall apart. It doesn't take millions of years. Often, it doesn't even take decades. A house that stands empty starts to rot almost right away. Rain seeps in, wood swells and splits. Insects chew through the walls. Mold spreads in the dark. Roof tiles come loose in the wind. Windows break. Weeds push through the floors. Before long, the whole place feels like it's sinking. This is just the beginning. Multiply that by centuries, then thousands of years, and what seemed like something built to last turns into dust. Now think about something larger: a skyscraper, a factory, a shipyard. These are made with metal and concrete, which sound much tougher. But even those have enemies: rain, salt, oxygen, heat, cold. These simple things are always working, always pulling apart the shapes we build. Metal rusts. It's a slow reaction, but it never stops. When iron meets water and air, it forms reddish flakes that grow and spread, eating away at the surface. Rust weakens beams, causes bolts to snap, and makes whole structures crumble. Stainless steel resists it better, but even that breaks down in the right conditions. Given enough time, even the thickest steel will return to the earth as powder. Concrete cracks. It absorbs water through tiny pores. When that water freezes, it expands, and the cracks get bigger. Salt from the ocean or roadways gets inside and speeds up decay. Inside many concrete buildings are steel rods meant to hold the weight. But when moisture reaches them, they rust and swell, pushing outward and breaking the concrete from within. This is called concrete cancer, and once it begins, it's hard to stop. After a few hundred years without care, Most concrete buildings collapse. Plastics seem more stubborn. They don't rust. They don't rot the way wood does. But plastics have their own weakness: sunlight. The ultraviolet rays from the sun break the bonds in plastic molecules, making them brittle. Over time, they crumble into flakes and then into microplastics. These tiny pieces can last longer, especially if they're buried or underwater, but their original form, the bottle, the bag, the casing, is gone. Electronics fall apart even faster. Inside our phones, computers, and machines are delicate parts made from copper, gold, silicon, and rare elements. These materials are finely structured and sensitive. Corrosion starts quickly. Heat and cold cause parts to expand and contract, breaking tiny wires. Batteries leak, moisture creeps in. Without repair or protection, the circuits that run our world fade out layer by layer. Imagine a city left behind, no people, no maintenance. In 10 years, plants would start to take over. Roots would push through pavement. Vines would climb walls. Insects, birds, and small animals would move in. Cracks would widen. Glass would fall. Paint would peel. Water would pool in basements. Mold would spread. In 100 years, most wooden buildings would be gone. Metal frames would be rusted through. Concrete would be falling in chunks. Streets would break apart. Trees would grow where cars once drove. In 1,000 years, only the strongest parts might remain. Some stone foundations, rusted shells of machinery, fragments of plastic buried under dirt. In 10,000 years, it's likely nothing would be left on the surface. Forests, deserts, or oceans would cover what was once there. Only the things buried deep or sealed off might survive. But even those are under pressure from time. If a metal car engine gets buried in mud, it might last longer. But the metal still reacts with the minerals around it. It oxidizes, it leaches. Little by little, it becomes part of the ground. The same goes for wires, circuit boards, and batteries. They don't last forever. Nature slowly pulls them apart. It's not just the physical materials. Even signs of energy fade fast. Light, heat, and sound leave no long-lasting trace. Radiation from power plants or bombs might linger in soil for thousands of years, but even that weakens over time. A future civilization could detect some isotopes, but only if they dig in the right place. One of the most fragile parts of our world is data. Our records, books, films, digital files, are the first things to vanish. Paper decays, film breaks down, hard drives fail in just a few decades, magnetic tapes lose their signals, flash memory corrupts. Unless information is copied and preserved again and again, it vanishes quickly. And if no one is there to read it, even what survives becomes meaningless. Stone carvings last longer. Some ancient texts on stone tablets are still readable after thousands of years. But in modern times, we don't use stone much. We store our knowledge in formats that need power and machines to access. If those machines stop working, the knowledge becomes unreachable. A computer without electricity is just a box of parts. A hard drive without software is just a piece of metal and glass. Over millions of years, the pressure of the Earth becomes the final eraser. Buried things get crushed. Crushed things heat up and melt. Sediments turn into rock. Most organic material disappears. Even many bones and shells are lost to time. Only the hardiest materials in the best hiding places become part of the record. This means that unless a previous civilization left something truly massive, like a giant pyramid made from diamond-hard material buried under miles of rock, it would be almost impossible to find. And even then, the forces of geology might still find a way to grind it down. Nature always reclaims what it's given. The Earth is not a museum. It doesn't keep things on display. It rebuilds itself over and over again. What survives is not always what's strong, but what's lucky. A plastic bead that sinks into the mud at just the right moment. A trace of metal sealed in a cave. A layer of chemicals frozen in ancient ice. These tiny leftovers might someday tell a story. But it will be a story with many missing pieces. Even if we built wonders greater than anything we can imagine currently, they would fade. Even if we reached the stars and touched other worlds, Earth itself might one day forget we were ever here. The silence of deep time is powerful. It does not care for memories. It only keeps what it must, and even that, only for a while. The Antikythera mechanism, a warning from the ancient world. In the year 1901, sponge divers off the coast of the Greek island of Antikythera stumbled upon something strange. Deep underwater, inside the remains of a sunken Roman-era ship, they found statues, coins, and broken pottery. But buried among the wreckage was something even more mysterious: chunks of corroded bronze covered in gears. At first, no one knew what it was. It looked like a lump of metal and rock, rusted and broken, with parts missing. It didn't match anything else from the ancient world. Most experts assumed it was nothing more than a piece of junk or a worn-out tool. It would take decades before the true nature of the object began to reveal itself. As technology improved, scientists used X-rays and CT scans to peer inside the corroded metal. What they found was stunning. The fragments came from a machine unlike anything ever discovered from ancient times. Gears, levers, and dials, carefully shaped and assembled. It was a kind of analog computer designed over 2,000 years ago, probably around 100 BCE. It could predict solar and lunar eclipses. It could track the movements of the sun, the moon, and possibly even the planets. It showed the phases of the moon and marked the cycles of the ancient Olympic Games. All of this in a box small enough to carry. Nothing else like it had ever been found from that time. Not in Greece, not in Rome, not in Egypt or Babylon. The level of craftsmanship and mechanical understanding required to build it was far beyond what historians believed the ancient world was capable of. And yet, here it was. Someone had made it. Someone had known how to cut precise bronze gears and arrange them in layers, all working together to model the heavens. The Antikythera mechanism became a riddle and a warning. This device was not lost in deep time, it was lost in shallow time. It had been sitting on the sea floor for 2,000 years, not 20 million, and even in that short time, it almost disappeared completely. If the sponge divers hadn't chosen that exact spot, on that exact day, and gone deep enough into the wreck, the mechanism would never have been found. The sea would have gone on slowly dissolving it. Fish and salt would have finished the job, and the ancient world's most advanced piece of engineering would have turned to dust, unknown forever. That fact raises a troubling thought. If a piece of technology this rare could almost vanish from a period of history that we know fairly well, what does that say about older periods we know very little about? The Antikythera mechanism didn't come from a forgotten civilization. It came from the same Mediterranean cultures we study in school. The Greeks, the Romans. Their writings, buildings, and stories have survived for centuries. And still, this one device took us completely by surprise. It wasn't mentioned in any ancient texts. No records explained how it worked or who built it. No second version has ever been found. For all we know, there may have been many such machines, some used by sailors, astronomers, or philosophers, but none survived. And without physical proof, no modern expert would have believed such a device existed. This is how the past hides itself. Not just through decay or disaster, but through silence. History doesn't always leave clear footprints. Sometimes it leaves nothing. If a few gears can disappear from a well-documented era, imagine what could be lost from times we barely understand. Civilizations that rose and fell long before writing. People who shaped tools, carved stone, built ships, or studied the stars, but left no evidence we can see today. The Antikythera mechanism suggests a gap between what once was and what we now know. It shows how even a small pocket of technical knowledge, if not widely shared or preserved, can vanish entirely. If it hadn't been built from metal, if it hadn't gone down with a ship, if it hadn't landed in a part of the ocean that eventually got explored, we would never have found it. There may have been other devices like it made of wood or bone, materials that rot quickly. There may have been scrolls explaining its use, lost to fire or mold. There may have been schools or workshops that made such tools, later destroyed by war, earthquakes or neglect. In that sense, the mechanism is not just a wonder, it is a ghost, a whisper from the past that nearly went unheard. And it shows how narrow our window of discovery really is. We only know what we can find, and what we can find depends on luck, survival, and where we choose to look. For every ancient object that ends up in a museum, there are likely hundreds that did not survive, or have not been unearthed. Entire lines of technology might have come and gone without leaving behind a single trace we can recognize. The Antikythera mechanism also changes how we think about progress. It breaks the idea that technological development moves in a straight line, from simple tools to complex machines, from stone to metal to microchips. Here was a device more advanced than anything built for over 1,000 years after its time. After the fall of Rome, the knowledge of how to make such a machine seems to have vanished. No one rebuilt it, no one copied it. The design was lost for centuries. That too is a lesson. Complexity does not guarantee survival. A brilliant invention can disappear if the people who understand it disappear. A civilization can forget its own past. Sometimes history moves backward. This one discovery also changes how we search. When we think of ancient ruins, we often picture temples, pyramids, or statues, big, obvious structures made of stone. But a device like the Antikythera mechanism shows that the most meaningful clues might be small. A gear, a dial, a piece of metal that doesn't match the time period. Something easily missed or thrown away. It tells us to look more carefully at what we already have. Some objects in museum collections might seem unimportant because they're too damaged or strange, but inside them could be stories we haven't yet uncovered. So what else could be out there? What other wonders might have existed, only to be lost to floods, fires, earthquakes, wars, or simple decay? The Antikythera mechanism is a reminder that advanced knowledge can slip through our fingers, that history is fragile, and that what we know is always less than what there once was. Even in the modern world, we are vulnerable to forgetting. If our society faced collapse through climate change, war, or disaster, how long would our technology last? How many of our machines would survive? How many books, files, or devices would still be readable in 1,000 years? What if we had to start over without power, industry, or tools? The past has already done this. The Antikythera mechanism is a piece of that story, not just of invention, but of loss. A warning from a time not so far from ours, showing how easy it is for knowledge to vanish and how hard it is to get it back. The bias towards simplicity in archaeology. When we think about the ancient past, most of the time we picture stone tools, broken pottery, and rough carvings. That's what fills museum displays. Arrowheads, scrapers, spear tips, clay jars. These are the items we use to understand the earliest stages of human life. And because these are the things we keep finding, it's easy to believe that ancient people lived simple lives with simple tools. But what we find isn't always a reflection of what once existed. Stone and fired clay last a long time. They're strong. They don't rust or rot. Even after thousands or millions of years, stone tools can still be found on riverbanks, in caves, or buried in layers of soil. But many other materials, wood, leather, bone, cloth, paper, don't survive well at all. They decay. They get eaten by insects or bacteria. And once they're gone, there's no way to know they were ever there. That creates a kind of silence in the record. We only see the durable things, and because of that, our idea of ancient life becomes biased towards simplicity. If someone made a wheel out of wood, it might not last. If they carved a gear, built a small boat, or used woven fabric, we might never see it. If they made drawings or blueprints on parchment or animal skin, those wouldn't survive either, at least not outside of rare, dry environments. So we're left with the things that last. Heavy things, tough things, things made of stone, baked clay, or sometimes metal if it didn't corrode. And when archaeologists dig through old layers, those are the kinds of artifacts that fill their trays. This creates an illusion. It makes it look like ancient people were only using stone tools because those are the tools we still have. But that doesn't mean that was all they had. In fact, there's good reason to believe they had a much wider range of tools and materials. We know that even very early humans were skilled with wood, sinew, and fibers. They made baskets, they built shelters, they crafted traps and nets. All of that required knowledge and planning, but because those items decay quickly, they barely show up in the archaeological record. This preservation bias means that the past is not recorded evenly. The soft parts, the delicate ones, get erased, and when we look only at what remains, we might make wrong assumptions. We might think people were less skilled or less advanced than they really were. Archaeologists are aware of this, but it's still hard to work around. After all, science depends on evidence. And when most of the evidence is missing, it's difficult to tell the full story. Still, some findings hint at the complexity that's often overlooked. There are footprints of tools made from wood or bone, impressions left behind in mud that hardened over time. There are marks on bones showing that tools were sharper than stone alone could achieve, suggesting other materials were used. In a few rare cases, wooden spears or woven fibers have survived in cold or dry environments, showing that ancient people had far more skill than stone tools alone would suggest. The problem grows bigger the farther back we go. The deeper the layer, the older the soil, the less survives. And it's not just about small objects. Even large structures can vanish. A house made of wood and grass will disappear within decades if it's left alone. Even if an entire village existed, it might leave no trace. There would be no rooftops, no fences, no furniture, maybe only a few fire pits or post holes in the ground. And if we didn't know what to look for, we might miss those too. Now think about the bigger picture. If an advanced group of people existed far in the past, long before known civilizations, and used tools that were mostly biodegradable, what would they leave behind? If they made machines from wood and fiber, if they wrote on leaves or bark, if they used natural materials instead of metal or stone, it's possible that no evidence would survive at all, especially if they were small in number, or if their time on Earth was brief. The bias towards simplicity makes us think of ancient people as primitive, but intelligence doesn't always leave a mark. A person who plans, solves problems, tells stories, or builds tools is intelligent, even if those tools are made of things that disappear. And this creates a kind of trap for researchers. They rely on the hard evidence, but the hard evidence is limited. It doesn't always reflect the full reality of the past. That's why the discovery of something like the Antikythera mechanism is so important. It shows that ancient people were capable of making highly complex devices, even if those devices rarely survive. And it forces scientists to ask, what else have we missed? What if we've been underestimating ancient minds because we've been over-relying on the few materials that last? This kind of bias shapes more than just tools. It also affects how we think about timelines. If we believe that advanced technology is rare in ancient history because we rarely find it, we might be ignoring the fact that such technology might just decay faster. We assume simplicity came first and complexity came later. But what if there were periods of complexity, followed by collapse? What if some groups reached high levels of knowledge only to vanish and take their tools and records with them? These questions are hard to answer, but they challenge the idea that we understand the past as clearly as we think we do. It also puts pressure on the way we search. If we only dig for stone, we will only find stone. If we design our questions around simple tools, we'll mostly find answers that support that view. But if we allow for the possibility that many things are missing, if we factor in decay, erosion, and loss, we might start seeing the gaps not as empty, but as hidden. Some archaeologists are looking more closely at signs of organic materials, soil stains, microscopic fibers, patterns of wear. They're using new techniques like residue analysis to detect what was once stored in broken pots. They're scanning sites with satellite imaging to find shapes buried deep underground. They're realizing that sometimes the absence of something is just as important as what's present. The bias towards simplicity doesn't mean we're wrong about everything, but it does mean we might be missing something big. Our ancestors weren't just survivalists with rocks and sticks. They were problem solvers. They adapted to their environment. They made choices. And some of them, maybe even long ago, might have created things that were smarter and more advanced than we ever imagined. But time is a thief, and nature is a slow destroyer. The deeper we dig, the quieter the past becomes. What we hold in our hands, the arrowheads, the pots, the bones, are only the strongest echoes. Carbon spikes and anoxic events. A smoking gun? Carbon shows up in different forms, sometimes from volcanoes, sometimes from dying plants and animals, and sometimes in our modern world, from burning fossil fuels. The carbon story isn't just about life, it's also about how that life shaped the planet. And sometimes it's about sudden, strange events. When carbon levels spiked fast, the climate changed, and the oceans started to lose their oxygen. These events are known as carbon spikes and anoxic events, and they may hold more secrets than we realize. One of the most famous of these ancient spikes is called the Paleocene-Eocene Thermal Maximum, or PETM. It happened about 56 million years ago. During the PETM, something caused a rapid and massive release of carbon into the atmosphere. Global temperatures soared by around 5 to 8 degrees Celsius. Oceans warmed. Sea levels rose. Some parts of the deep ocean lost their oxygen. Whole ecosystems shifted. Animals moved toward the poles. Coral reefs struggled. Some species vanished. And in the rock record, all of this shows up as a thin band of clay-rich sediment with a sharp drop in a certain carbon isotope called carbon-13. This drop tells us that the carbon entering the system was light, meaning it came from organic sources, like plants, soil, or methane, rather than volcanoes or other geologic processes. That makes it similar, at least in chemistry, to the carbon we're adding to the atmosphere today through burning fossil fuels. In fact, when scientists compare modern carbon data with the PETM, they often call it the best historical match we have. It's the closest thing in Earth's past to what's happening now. But here's the strange part. We still don't know exactly what caused the PETM. There are ideas. Some scientists think it might have been a slow but steady warming from volcanic activity that triggered the release of methane from the ocean floor. Others suggest it was a sudden event, like a massive earthquake or underwater landslide that disturbed methane hydrates. Still others point to changes in ocean currents, the movement of continents, or even large-scale wildfires. But so far, no single theory explains it all. Something big happened, something fast, and something left a mark that has lasted for millions of years. That opens the door to a question that's hard to ignore. Could a past civilization have caused it? What if a species, long before humans, had reached a point where it could burn fossil fuels? What if it developed energy systems based on coal or oil? What if it changed the land, cleared forests, and built machines? Over time, such a civilization would pour carbon into the atmosphere just like we're doing now. And in the rock record, that would look almost exactly like a natural carbon spike. This is what makes the PETM and other carbon spikes so interesting. They force us to look closer. Were there chemical markers beyond carbon? Was there a rise in metals, plastics, or artificial compounds? Were there strange shifts in the food chain, or patterns in extinction that hint at more than just warming? So far, we haven't found those extra signs. But then again, we haven't looked everywhere. Most of our attention goes to land-based fossils, but the best records often lie at the bottom of the sea. And the PETM isn't the only event like this. There are others. One example is the Torsion Oceanic Anoxic event, about 183 million years ago. Another is the End Permian extinction, around 252 million years ago, the largest mass extinction in Earth's history. Each of these involved rapid carbon input, warming oceans, and the death of many species. And in each case, we still debate the exact causes. Some show patterns that could be linked to volcanic activity, huge outpourings of lava that released gases over thousands of years. But even in those cases, the chain of events isn't fully clear. Could there have been a trigger? Could something other than volcanoes or methane have set the process in motion? When we look at events like the PETM, the Silurian hypothesis becomes more than just a thought experiment. It becomes a challenge to our methods. How do we separate a natural carbon spike from an artificial one if all the obvious artifacts have vanished? There are a few ideas. One involves isotopes, looking not just at carbon, but at other elements that might behave differently depending on their source. Another involves searching for signs of synthetic compounds. But this requires deep drilling, high-resolution chemical scans, and a willingness to think beyond the usual explanations. Even without a past civilization, these questions matter. They help us understand what our own mark on the planet will look like. They show how long Earth takes to recover from a shock. And they remind us that we're not the first to change the world in a big way. Nature has done it too, and often more violently. But if something else was here before us, something clever, industrial, and short-lived, we may already be looking at their footprint. We just don't realize it yet. Civilizations without cities, a possibility we rarely consider. When we think about advanced civilizations, our minds often go straight to cities, skyscrapers, roads, power lines, and dense urban centers. That's how we live now, and so we imagine others would live the same way. But what if that's not the only path? What if a civilization could grow advanced without ever building a single city? It sounds strange at first. Cities feel like a natural result of progress. They bring people together, help organize labor, allow for trade, and foster invention. But this idea is based on our experience, on how humans developed agriculture, settled down, and built permanent structures. It's shaped by the way our species chose to live. That doesn't mean it's the only option. There's no law of nature that says technology requires skyscrapers. There's no rule that says intelligence must gather in stone or concrete clusters. In fact, looking deeper into how we evolved, it becomes clear that most of our history wasn't lived in cities at all. For hundreds of thousands of years, humans lived in small bands. We moved with the seasons. We hunted, gathered, shared knowledge, and passed down stories long before we ever stacked bricks or carved roads. Even today, many human inventions can travel without cities. Think of the smartphone in your pocket. It may have been designed in a lab or factory, but once it leaves that space, it functions on its own. Information is shared through satellites. Energy can come from solar panels or batteries. In theory, an intelligent species could develop similar tools that don't depend on fixed buildings or crowded centers. A civilization like that could be mobile. It might move across open landscapes, following resources. It might live on the ocean, drifting in large rafts or seaborne communities. It might even stay small by choice, favoring balance with nature over expansion. Instead of growing upward, it could grow inward, focusing on knowledge, art, or internal systems of energy and communication. These people might master materials that biodegrade naturally. Their tools might be built to disappear. Their energy sources might leave no trace. Such a way of life would be almost invisible from a geologic lens. Without stone foundations, wide roads, or huge waste dumps, the physical remains would vanish fast. Even things like metal tools or storage vessels, if made from organic material or light alloys, might not survive more than a few thousand years, let alone millions. And if their footprint was scattered, never focused in one place for long, the chances of finding a clear signature drop even lower. We can already see hints of this idea in our world today. In the Amazon rainforest, discoveries made using ground-penetrating radar have revealed the layout of ancient villages and roads that were hidden under the trees. These settlements were large, organized, and complex, but they left behind almost nothing visible above ground. If it weren't for modern technology, we might never have known they existed. And they're only a few hundred years old. Now stretch that kind of invisibility across millions of years. Imagine a culture that lived in harmony with the ocean, traveling in fleets that left no port. Or think of one that thrived in ice-bound environments, building with snow, bone, or hide. These materials vanish fast. Even their garbage could decompose into soil. Their structures could collapse and blow away. Their paths would fade like footprints in sand. Archaeology is good at finding things that are buried, heavy, or burned. It struggles with things that are light, fragile, or spread thinly across large areas. Our methods are built on digging, not drifting. They depend on ruins. So if a civilization chose to live lightly on the planet, by design or by chance, it could be almost undetectable today. Some scientists have even speculated about civilizations that live almost entirely in the sea. The ocean covers over 70% of Earth's surface. It holds the largest living space on the planet and some of the oldest life forms. Whales, dolphins, and octopuses already show signs of advanced problem-solving, memory, and communication. Could something more have evolved there long ago? Something we haven't found because we haven't looked in the right way. An ocean-based civilization might never leave behind traditional ruins. No buildings, no fire pits, no roads. Their tools could be made of shell, bone, or coral. Their waste could be carried away by currents. Even if they had energy systems or networks, those might use sound, light, or pressure in ways that leave no chemical trace. And if they eventually vanished, swallowed by the sea, their story might be gone forever. It's also possible that a civilization could avoid cities for spiritual or philosophical reasons. Maybe they saw cities as dangerous, too rigid, too crowded, or too destructive. Maybe they believed in living with the land, not shaping it. They could still share ideas, build machines, and explore the stars, just without paving over nature. Instead of monuments, they might have focused on internal knowledge. Their history might have been passed down orally or stored in devices designed to disappear when no longer useful. Even among modern humans, this kind of thinking exists. Some groups have chosen to live without modern tools or buildings. Others use advanced knowledge to build in ways that are eco-friendly, modular, or biodegradable. These decisions often come from values, not limitations. If we imagine a civilization shaped by different values, ones that don't prize permanence or scale, then their traces might be as thin as dust. A mobile or scattered civilization could last thousands of years and still leave almost no clear mark. If they were wiped out by a natural disaster, their remaining evidence might be quickly buried or lost. And if they never dug mines, built dams, or leveled forests, the planet itself might have healed over their existence. To future scientists, it would look like they were never there at all. Our assumptions shape what we search for. If we only look for pyramids, factories, or roads, we'll miss anything that doesn't fit that mold. The Earth is full of blind spots, places we haven't studied deeply, and periods of time where little remains. Biological proxy, or technosignature. When we see a sudden change in the fossil record, like a new body shape or a new behavior, it's usually seen as natural evolution. A species adapts to its environment, finds a new food source, or avoids a new predator. That's the story we've told for over 100 years. But what if that story isn't always complete? What if some changes weren't natural at all? Evolution is one of the most tested ideas in science. It explains how life grows and changes and why some forms survive while others disappear. But evolution also works slowly over long stretches of time. So when we see sharp, sudden jumps in biology, it raises questions. Sometimes these jumps are explained by chance events, a mutation, a climate shift, or a comet strike. Other times, they're harder to explain. This is where the line between biology and technology becomes blurry. If a species had the tools to change DNA on purpose, if an ancient civilization could edit genes, shape life, or guide evolution, would that leave a trace? Or would we see the results and assume they came from nature? Scientists call this kind of evidence a technosignature, a clue that shows technology was used. It's the opposite of a biological proxy, which is a natural sign that something changed through normal life processes. The problem is, these two can look very similar. For example, a shift in DNA might happen because of a random mutation. But the same shift could also be caused by genetic engineering. There are already moments in Earth's history where things changed fast and deeply. One of them is the Cambrian explosion, around 540 million years ago. Before that, life was simple, tiny and slow-growing. Then, in a short time, many new body types appeared, creatures with shells, eyes, limbs and teeth. It was a leap unlike anything seen before. Most scientists think this was a natural process. There are a few common explanations. One is that life before the Cambrian was mostly soft-bodied. Creatures without bones, shells, or tough outer layers don't fossilize easily. So even if they existed, their remains wouldn't show up in most rock layers. This means the missing record might not mean the life wasn't there, it just wasn't preserved. Another explanation is that environmental changes helped trigger the explosion. Oxygen levels in the oceans rose, new food chains may have formed. Predator-prey relationships could have pushed animals to evolve rapidly. These factors might have worked together, causing life to suddenly grow more complex. But even with these ideas, the Cambrian explosion still feels like an odd break in the timeline. It's like reading a long book and suddenly discovering a chapter that seems to start in the middle of a new story. The build-up, the gradual changes, the missing bridge between the simple forms before and the complex ones after, it's mostly gone. So people have asked, what if something else helped push it along? If a civilization had existed at that time, it might have been interested in shaping life. It could have tested new designs, altered existing species, or boosted development in certain directions. Even if they meant no harm, their actions could have changed the course of biology forever. But if they vanished afterward, we would have no direct evidence. We would only see the results. Some animals seem to appear suddenly, without clear ancestors. Others carry traits that seem too advanced for their time. Cephalopods, like octopuses, are often mentioned in this context. They have large brains, color-changing skin, and complex problem-solving abilities. Their DNA is strange, with many genes not found in close relatives. Could this be a sign of artificial influence? Or is it just nature's way of trying new forms? We also see sudden die-offs in the fossil record. Sometimes these are linked to volcanoes or asteroids. But what if, in rare cases, they were caused by technology? A civilization might have tried to reshape the planet and failed. It might have created synthetic organisms that outcompeted natural ones. It might have triggered ecological collapse by accident. These would all leave biological traces, but no clear fingerprints. The challenge is in the tools we use to study the past. DNA can survive for tens of thousands of years, but not millions. Fossils give us the shape of bones or shells, but not the inner story. Chemical clues can show sudden changes, like a burst of carbon or a drop in oxygen, but they don't tell us why. So we build models and test ideas. But models are based on assumptions, and if one of those assumptions is wrong, then we might miss something important. It's worth noting that even today, humans are changing biology in ways that future scientists might not recognize. We edit crops to resist insects. We engineer bacteria to make medicine. We modify animals for research or farming. If our civilization ended tomorrow, and others studied Earth 100 million years from now, would they know these changes were intentional? Or would they seem like just another part of evolution? A genetically modified plant might leave behind pollen that looks different. A farm-raised animal might have unusual traits. A lab-grown microorganism might spread into the wild. But without context, these might be hard to flag. The DNA would look strange, but not necessarily artificial. And if the tools used to make them were lost or broken down, the story would be hard to trace. This problem grows even more complex when we imagine civilizations that were careful, ones that edited genes without leaving waste, or used organic tools that decomposed. Their influence could ripple through ecosystems without leaving physical signs. In fact, the cleaner the technology, the harder it would be to detect. In this way, advanced knowledge might hide itself. Not every biological shift would be caused by control. Some might be side effects. For example, pollution can alter the way animals grow or reproduce. Chemicals in water can affect hormones or behaviors. If an old civilization dumped synthetic material into the environment, that alone could change biology. Later, these shifts might show up in fossils, but again, they'd look natural. A scientist studying them today might see only adaptation, not interference. If intelligence can leave traces in biology, what kinds of patterns would count as artificial? Repeating DNA sequences that serve no known function? Sudden complex traits with no clear path? Behaviors that appear far before the brain should allow it? Each of these could hint at something more, but without proof, they remain only suggestions. We are just beginning to develop tools that can scan ancient DNA for oddities. As technology improves, we may find more clues hiding in the genetic code. And we may need to rethink what counts as natural. Because in deep time, biology and technology can look almost the same. One grows slowly, the other can leap. But after millions of years, all that's left is the shape of the leap and the mystery of where it came from. Deep oceans, our civilization's final resting place. The open ocean stretches across most of the planet. From horizon to horizon, it's a place that feels endless. But what lies beneath is even more mysterious. The deep ocean remains the least explored part of the world. It's dark, cold, and under immense pressure. For thousands of years, humans could only guess what was down there. Even now, with modern submarines and sensors, we've only scratched the surface. But one thing is clear. The ocean floor is where much of our world's debris eventually ends up. It may also be the final resting place for the story of our civilization. When objects are thrown into the sea, whether by accident, disaster, or design, they often don't stay near the surface. Metal sinks, plastic drifts and clumps together, and heavy debris like concrete and glass makes its way slowly downward. Over time, these things settle on the seabed. But the seabed is not just a flat, empty space. It's layered with sediment, mud, dust, organic material, tiny shells, and minerals that fall like snow from above. These layers build up over time, slowly burying whatever lands there. In some parts of the ocean, especially near river mouths or coastlines, sediment builds up fast. Storms, floods, and landslides wash tons of particles into the water. In other regions, far from land, the sedimentation is slower but still steady. Microscopic plankton die and drift downward. Volcanic ash from distant eruptions settles across the ocean floor. Even dust blown from deserts can end up there. Over thousands of years, these layers can become very thick, sometimes hundreds of meters deep. And once something is buried under that much material, it becomes very hard to find. This means that the deep ocean acts like both a graveyard and a time capsule. It buries things slowly but thoroughly. And because it's cold and low in oxygen, decay happens much more slowly than on land. Some shipwrecks that would have rotted away in a river or shallow bay are preserved surprisingly well at great depths. Wooden hulls stay intact for centuries. Cargo holds keep their shape. Even the Titanic, sunk more than 100 years ago, still lies in place 2 miles beneath the surface, though rust and bacteria are slowly eating away at it. But while the ocean might preserve things longer, it also hides them better. The darkness, pressure, and distance make it hard to study. Most of the equipment used to explore the sea floor can only survey small areas at a time. Even with sonar and submersibles, finding something is like searching for a needle in a haystack. The deeper you go, the harder it becomes. Some regions have never been explored at all. Others have only been mapped in a general way, good enough to see mountain ranges or trenches, but not to spot small objects or buried materials. If we think about future archaeologists or geologists 100 million years from now trying to study our time, the ocean floor would hold a lot of clues. Ships, submarines, containers, cables, and plastic waste are all there already. Some of our deepest garbage dumps are unintentional. Discarded military equipment, crashed satellites, leaking barrels, and even human remains have ended up in the sea. All of it drifts down, layer by layer, becoming part of the long geological record. But whether these things survive long enough to be found is another question. In many places, tectonic plates meet under the ocean. One plate dives beneath another, creating trenches and volcanoes. These subduction zones are where the seafloor gets recycled, so even in the deep ocean, some parts of the crust are temporary. Other areas are more stable, like the abyssal plains. These are wide, flat regions of the deep ocean where sediment builds up slowly but steadily. In these places, an object that sinks to the bottom might be buried gently, without being disturbed by earthquakes or heat. If a city's remains were somehow dumped in one of these plains, perhaps due to a massive flood, a slow sinking, or even deliberate effort, it might be covered and preserved for a very long time. But finding it later would be nearly impossible unless someone knew exactly where to look. Another challenge is that deep-sea sediments, once hardened into rock, are hard to drill through. Core samples, cylinders of layered mud and clay pulled up by research ships, only go down so far. They might capture the top few meters of sediment, but not the hundreds of meters below. Most of what lies deeper remains untouched. If there were unusual layers, they might still be down there, out of reach. Some scientists do look for signs of human activity in the ocean's sediments. They've found microplastics, synthetic fibers, and bits of industrial ash in layers deposited over the last century. These are considered part of the evidence for the Anthropocene, but they're also fragile. A strong underwater current, a deep-sea earthquake, or even a slow change in ocean chemistry could scatter or destroy them over time. The salt, pressure, and slow biological activity of the deep sea can wear things away. Unless something was made of some unusually durable metal, it might not last more than a few thousand years. After 1,000,000 years, it might leave nothing behind. And yet, strange things do sometimes appear. Odd metallic spheres, out-of-place artifacts, or puzzling patterns in sediment layers occasionally spark questions. Most of these turn out to have natural explanations, or are the result of modern contamination. But the possibility remains. If we found something unexpected in the deep ocean, something that didn't match known geology or biology, it might be a clue from a time we've forgotten. Time capsules in unlikely places. There are places on Earth that act like vaults, hiding away pieces of the past. These places weren't built, but because of their unique conditions, lack of water, extreme cold, or total darkness, they end up preserving things far longer than they should normally last. Frozen ground, especially in the far north, is one of the most surprising protectors of the past. Permafrost, which is soil that stays frozen year-round, covers large parts of Siberia, Alaska, and Canada. For tens of thousands of years, it has locked away the remains of mammoths, ancient plants, and even the bodies of prehistoric humans. These remains often come out in astonishing condition. Soft tissue, fur, and even stomach contents can still be studied. Scientists have found mammoth meat that looked like it had just been frozen, despite being over 30,000 years old. In rare cases, viruses and bacteria trapped in the ice are still intact, and sometimes even alive. This kind of preservation isn't perfect. Freezing and thawing can damage tissues, but it's far better than what happens in warmer regions. What makes permafrost so powerful is its cold and dryness. Decay slows down dramatically in such conditions. Microbes that would normally break down tissues can't survive. In places like the Siberian tundra, things don't rot, they just stop. If a civilization had once existed during an earlier ice age, and if some of its materials had ended up buried in frozen ground, they might still be there now. The challenge, of course, is getting to them. Permafrost is remote, buried, and now starting to thaw in many places due to climate change. But as it melts, new discoveries are being made. Bones, tools, and even mummified animals are being uncovered. Another place that surprises people is deep caves. These underground worlds are cold, dark, and stable. Some have gone undisturbed for millions of years. Caves don't have wind, rain, or sunlight. Their air doesn't change much. This makes them ideal for preserving carvings, bones, or tools. In parts of Europe, caves have protected cave paintings and handprints made by early humans more than 30,000 years ago. The pigments used were simple: charcoal, minerals, and ochre, but they're still visible, drawn across the walls of stone chambers that no light has touched in ages. In dry caves, especially in desert regions, preservation is even better. Egypt's Valley of the Kings, for example, is one of the most famous time capsules in the world. Because of the dry climate and deep burial, wooden coffins, papyrus scrolls, linen bandages, and even dried food have survived for thousands of years. This kind of dryness stops the growth of mold and bacteria. It's one reason why deserts are among the best places to find ancient relics. But deserts also shift. Sand covers and uncovers ruins. Winds erase footprints and smooth down sharp edges. So, while things can last longer, they can also stay hidden for centuries without anyone noticing. One of the most extreme examples of preservation happened in the Atacama Desert in Chile. This is one of the driest places on Earth. Some parts have not seen rainfall in recorded history. Here, ancient mummies were naturally preserved without any embalming. The dryness sucked moisture from their bodies, leaving behind skin, hair, and clothes in nearly perfect condition. If a more advanced civilization had existed there long ago, and if it left behind technology made from organic materials, it's possible those items might still be hidden beneath the sand. Tar pits are sticky black pools that form when oil seeps up through cracks in the ground. Over time, they trap animals, plants, and anything else that gets too close. In Los Angeles, the La Brea tar pits have captured bones of mammoths, saber-toothed cats, wolves, and even insects. The tar is thick and slow, but once something sinks in, it's sealed off from air and decay. Tar preserves bones in a dark, oily shell, making it harder for bacteria to reach them. These pits aren't common, but where they do exist, they can act like accidental vaults, holding fragments of lost ecosystems. Then there's the ocean again, but in a different way. We've already looked at the deep sea as a graveyard, but shallow, low-oxygen zones can also preserve material in an unusual way. In the Black Sea, for example, shipwrecks have been found in surprisingly good shape at depths where oxygen levels are too low to support most life. Without worms, bacteria, or scavengers, the wooden hulls don't rot. These wrecks lie where they sank, their contents untouched for centuries. Some are so well preserved that ropes, sails, and cargo are still in place. But not all time capsules are on Earth. Some people think the best time capsule for humanity is already beyond our planet. The Moon, unlike Earth, doesn't have weather, oceans, or tectonic plates. Its surface barely changes. Footprints from the Apollo missions are still exactly where they were made in 1969. Without wind or water, there's nothing to erase them. A civilization that left tools or machines on the Moon would find those objects sitting there unchanged, even after millions of years. No rust, no rot, just silent, airless cold. If a future species, either from Earth or elsewhere, visited the Moon and explored its surface carefully, it might find those artifacts exactly as we left them. That makes the Moon one of the most reliable places in the solar system for preserving history. Even a crashed satellite, a buried sensor, or a forgotten lander might become a message to the future. Mars is another possibility, though a little more hostile. Its winds can shift dust and sand, and its temperatures are harsh, but it's still more stable than Earth. If a future civilization builds time capsules, it might choose Mars or the Moon, not just for their symbolism, but because they don't erase history the way Earth does. The mysterious Ediacaran biota. The Ediacaran biota is one of the strangest chapters in the history of life on Earth. These organisms lived between roughly 635 and 541 million years ago, right before the Cambrian explosion. They were some of the first large and complex life forms, and their fossils have been found in places like Australia, Russia, Canada, and Namibia. But the creatures they left behind don't look like anything that's alive today. Some were shaped like leaves or feathers, some looked like discs or tubes, and others had strange ribbed bodies that defy easy comparison. For decades, scientists have debated what these organisms were and what they tell us about the early evolution of life. In textbooks, they are often called enigmatic or puzzling. That's because we still don't know whether they were animals, fungi, giant single-celled creatures, or part of a completely separate branch of life that went extinct. Some had no mouth, no gut, and no obvious way to move. Others seem to grow in ways not seen in modern life. Even the way they fed is uncertain. Some may have absorbed nutrients through their skin. Others may have relied on bacteria living on their surfaces. There's no clear answer, and that uncertainty has made them one of the most debated groups in paleontology. What makes the Ediacaran biota even more mysterious is how they appear and then vanish. For millions of years, these creatures seem to dominate the seafloor. Then, as the Cambrian explosion begins, they mostly disappear. Some researchers think they were wiped out by the rise of more active, mobile animals that outcompeted them. Others suggest environmental changes, like falling oxygen levels or shifting ocean chemistry, may have played a role. But the clean break between Ediacaran life and Cambrian life has led some to ask whether this was simply a failed experiment in complexity, or was it something else entirely? One idea is that the Ediacaran organisms were an early attempt by life to become multicellular and complex, but one that didn't quite work out. Their body plans didn't lead to anything we see today. Their strange forms may have made them ill-suited for the new, more competitive world of the Cambrian. In this view, they were a side branch in the tree of life, an evolutionary detour that ended in a dead end. But others think we're missing the bigger picture. Some of the Ediacaran fossils show signs of complexity that's hard to explain. Take Dickinsonia, for example, a flat, oval-shaped creature with a series of segmented ridges. For years, scientists couldn't even agree on whether it was an animal, a fungus, or something else. Recent chemical analysis showed traces of cholesterol-like molecules in some fossils, which suggests an animal origin. But that doesn't answer the bigger questions about how it lived, how it moved, or how it fits into the story of life. There's also Sprigina, which looks almost like a flattened trilobite, but without hard parts. Some think it might be an early arthropod or a close relative. Others argue it was something completely different. The point is, many Ediacaran organisms seem to have no clear modern descendants. They appear, exist for millions of years, and then vanish without a trace of continuity. The seafloor where many Ediacaran organisms lived was soft and muddy, which helped preserve their delicate bodies. But if other kinds of organisms existed elsewhere, say in different habitats or with different body structures, we might never know about them. So it's possible that our picture of the Ediacaran world is deeply incomplete. There's also another, more unusual possibility that some have quietly raised. Could some of these strange forms be misunderstood because we're looking at them with the wrong assumptions? When scientists study fossils, they often compare them to living creatures. They look for things like symmetry, organs, or known patterns of growth. But if something lived in a completely different way, if it had a body structure or a form of metabolism unlike anything we've seen, how would we even recognize it? Some researchers have even speculated cautiously that the Ediacaran biota might not all be purely biological in the way we think of it. Could some of the patterns in the fossil record reflect behaviors that were more organized than we assume? Could some of the growth forms be signs of collective action or environmental manipulation rather than individual organisms? These ideas are far from mainstream, but they reflect how little we truly understand about this chapter of Earth's history. It's also worth asking, why were these creatures so large compared to earlier life? For billions of years, life had been mostly microscopic. Then, during the Ediacaran period, suddenly we see organisms that are centimeters or even meters in size. That's a huge jump. To grow large, life needs enough energy and the right environmental conditions. One theory is that rising oxygen levels in the oceans allowed organisms to grow bigger. Another is that some of these creatures used novel strategies to feed and grow. But size alone doesn't explain their forms. Many Ediacaran fossils have complex fractal-like shapes. Fractals are patterns that repeat at different scales. Some Ediacaran organisms seem to be built almost entirely out of these repeating units. That's not how most animals grow, it's more like the structure of certain plants or crystals. So again, we're left asking, are we looking at life forms that simply followed a different set of rules? If we consider that possibility, then other questions open up. Could the Ediacaran biota represent not just a different branch of life, but a different style of life? One that used different principles for building bodies, interacting with the environment, or even reproducing? If so, they may have been successful in their own time and place, but ill-suited for the world that came after. Or perhaps they were more than we realize, and we just haven't found the right clues. The Ediacaran biota is like a message written in an unfamiliar language, carved into stone by a vanished world. They remind us that the history of life on Earth is not a straight line. It's a web full of dead ends, strange paths, and hidden stories. Whether they were a failed experiment, a different style of life, or something even stranger, they hold a lesson. The deep past is full of surprises. And some of those surprises might be more than just biological oddities. They might point to ways of living, growing, and evolving that we haven't yet imagined. Alien evolution on Earth, a speculative detour. The most famous creatures of the distant past are, of course, the dinosaurs. They ruled the planet for around 160 million years. By comparison, humans have only been here for a blink, about 300,000 years. Dinosaurs came in all shapes and sizes. Some were small and fast. Others were huge and slow. Many had sharp claws and advanced eyesight. Some, like the raptors, had large brains for their size. Birds, which are their descendants, still show signs of complex behavior today. Crows solve puzzles. Parrots use tools. Could something similar have started happening tens of millions of years ago in a dinosaur lineage? Let's imagine a small feathered dinosaur with a sharp mind, something like a troodontid. Troodontids were light, quick, and had one of the highest brain-to-body ratios among dinosaurs. If evolution had pushed just a bit further in the direction of intelligence, could they have become more than just smart predators? Could they have learned to manipulate objects? Build nests, not just from twigs, but with care and purpose? Share knowledge across generations? It's all speculation, but intelligence isn't tied to humans alone. Evolution doesn't favor one outcome, it explores many. If some group of creatures, whether dinosaur, reptile, or even something more ancient, had developed advanced thinking and behavior, what would that look like? Human intelligence is shaped by speech, writing, and memory. But that's not the only way a mind can work. An ancient species could have developed a different kind of intelligence, one based on scent, touch, light, or even chemical signals. It might not look like anything we would recognize. If we saw the remains of their behavior, we might dismiss it as random patterns or natural formations. Even today, we struggle to understand the minds of other animals. We know whales sing complex songs, but we don't know what they mean. We see bees dance to tell others where food is, but we don't know how much information they really pass along. There could be types of intelligence all around us that we barely notice. So when we look back through time, we have to accept that our tools, our expectations, and our ways of thinking all shape what we see. If we assume that intelligence always looks like us, bipedal, tool-using, city-building, we may miss other paths entirely. The Earth has had billions of years to play with life. In all that time, perhaps more than one intelligent species has risen and fallen. Perhaps one lived during the time of the dinosaurs, or maybe even earlier. The Silurian hypothesis and the Fermi paradox. The silence of the stars has always been strange. We look out into the night sky and see billions of galaxies, each with billions of stars. Many of those stars have planets. Some of those planets may be like Earth, with water, warmth, and the right ingredients for life. And yet, despite all those chances, we haven't seen any clear sign that anyone else is out there. This puzzle is called the Fermi paradox. It asks a simple question. If life is common in the universe, why haven't we found any signs of it? There are many possible answers. Maybe intelligent life is rare. Maybe it destroys itself before it can reach the stars. Maybe it chooses to stay quiet. Or maybe we're not looking in the right way. But one idea that has gained attention in recent years adds another layer. What if we don't even notice intelligent life when it appears, because it vanishes before it can leave a lasting trace? The Silurian hypothesis raises a larger point. If Earth itself can lose track of its past, if tectonic plates can erase continents and oceans can bury entire ecosystems, then our own history might be far from complete. If intelligence arose here once before and all the traces were erased, then it might not be strange that we haven't found it. It might just be what happens, again and again. Civilizations rise, change their world, and fall. After a few million years, the evidence is gone. Now bring that idea to the stars. If Earth, a planet we can study closely, might hide an ancient civilization from its own history, then what about other planets? When we scan exoplanets for signs of life, we're looking at their atmospheres, their light signatures, and maybe their heat. But if a civilization had risen and fallen a billion years ago, would we ever know? The light we see from those planets shows us their present, not their past. And if their history is as easy to erase as ours, then we might miss their story entirely. This idea creates a bridge between the Silurian hypothesis and the Fermi paradox. The silence we hear in space might not mean nothing happened. It might mean something did happen, then vanished. Civilizations might be like sparks. They light up for a moment, then fade. If their ruins don't last, and their signals never leave their home systems, then they would never be seen by anyone else. Each world could have its own story, but those stories would remain locked away. Humans often think of intelligence as a path to long life, but it might not be. Intelligence allows species to change their environment quickly. That can lead to industry, machines, and technology, but it can also lead to problems: pollution, war, or climate collapse. If the lifespan of a civilization is short, then the chances of two existing at the same time and noticing each other go down. The window for communication becomes small. This makes the quiet universe feel less like a mystery and more like a pattern. It suggests that maybe intelligence isn't rare, but long-term survival is. And maybe part of that has to do with memory. If civilizations don't leave strong records behind, then even they might forget themselves. A future intelligent species on Earth could study the planet and think it had never happened before, just as we now think we're the first. In many parts of the world, ancient cities have been lost for centuries under jungles, deserts, or even modern towns. We sometimes find them by accident, through satellite images or local legends. And these are ruins only a few thousand years old. Stretch that to millions of years, and the odds drop sharply. The stars may not be silent because no one is there. They may be silent because everyone is eventually forgotten. How this changes the Drake equation. The Drake equation is one of the most well-known tools in the search for extraterrestrial life. It was introduced in 1961 by astronomer Frank Drake, not to solve the problem of alien contact, but to organize our thinking about it. The equation isn't meant to give one final answer. Instead, it breaks the question down into smaller steps, into parts we might be able to estimate. Things like how many stars are formed, how many planets might support life, and how many of those might develop intelligent civilizations that can send signals into space. At first glance, it looks like a math problem, but behind each term is a mystery. And the last two terms in particular, how long civilizations last and how easy they are to detect, carry the most weight. Because if intelligent life is common, but never lasts long or never leaves a trace, then even a galaxy full of civilizations could still look empty to us. If a civilization existed on Earth millions of years ago and left no obvious signs, then the same could happen elsewhere. One of the terms in the equation is usually written as L, the length of time a civilization sends out detectable signals. For decades, this term has caused the most debate. Some argue it could be thousands of years. Others think it might be only a few hundred or even less. Now imagine that a civilization doesn't leave any clear radio signals at all. Or it does, but only for a short time. Maybe it switches to something else. Laser communication, encrypted bursts, localized networks. Or maybe it turns inward entirely, losing interest in broadcasting across space. In that case, even if it lasts for 1,000,000 years, we'd never know it was there. Now add the idea that it could vanish without a trace. That even if it built cities, flew planes, dug mines, or changed its atmosphere, the signs might not survive the crushing effects of time, geology, and erosion. That changes not only how long the civilization exists, but how long it's detectable. The two are not the same. A civilization could last for thousands of years, yet be detectable for only a fraction of that time. It also means the concept of detectable has to stretch beyond just signals. In the 1960s, people assumed aliens would beam out strong radio waves, maybe even point them at us, but that was before we realized how easy it is to lose something in the noise. The galaxy is full of static, radiation, and bursts of energy. Picking out one narrowband signal is like finding a whisper in a thunderstorm, and if that signal stopped long ago, we wouldn't even hear the echo. Some scientists have begun talking more about technosignatures, but even these might not last long. If the lifespan of detectable civilization is often short, and if the fraction of civilizations that produce detectable signals is low, then the final number, how many civilizations we might see right now, drops dramatically. This fits with what we observe. When we listen for signals, we hear nothing. When we look for ruins in our own solar system, we see only dust and rock. Out of billions of years of galactic history, the window where two intelligent civilizations exist at the same time, can send signals, and can detect each other might be incredibly narrow. Maybe so narrow that it almost never happens. Maybe the galaxy was once full of intelligence, but it came and went. Civilizations might flare up, shine brightly for a moment, and then vanish. And without long-lasting markers, each one becomes invisible. Time acts as a filter. Only the most durable signals remain, and even those fade fast. Looking for fossils in exoplanet atmospheres. Right now, our best tools for exploring distant worlds are telescopes. Some are in orbit, like the James Webb Space Telescope, and others sit on mountaintops. They can't take close-up pictures of faraway planets. But they can study their light. When a planet passes in front of its star, a little of the star's light passes through the planet's atmosphere. That thin layer filters the light in specific ways, depending on what gases are present. By studying that filtered light, scientists can figure out what the planet's air is made of. This method, called spectroscopy, has already revealed atmospheres with water vapor, carbon dioxide, and even methane. These are important because they can be linked to life. On Earth, for example, living organisms play a big role in shaping the atmosphere. Plants give off oxygen, animals breathe it in and release carbon dioxide. Microbes produce methane. All of these gases can be biosignatures. But what about intelligent life? A planet could have forests, oceans, and animals and still never develop technology. Civilizations, the kind that use tools and build machines, are something else entirely. So how would we tell the difference? On Earth, we produce lots of artificial gases. Some of them are rare or unstable, like chlorofluorocarbons or CFCs. These chemicals were made for things like refrigerators and air conditioners. They don't exist in nature. If you found them in a planet's air, you'd know someone put them there. CFCs are especially interesting because they're easy to spot, at least in theory. They have unique fingerprints in light. Even after humans banned most of them, they remained in the air for decades. If an alien world used something like CFCs, we might see the evidence for some after the civilization was gone. They would be, in a way, fossils, chemical fossils floating in the sky. Other possible technosignatures include nitrogen dioxide, sulfur hexafluoride, and industrial forms of carbon compounds. On Earth, we release these gases through mining, manufacturing, and energy production. In small amounts, they might be hard to spot. But if a civilization were large and active, the buildup could be noticeable, even from light years away. The trick is separating these signs from natural ones. Planets with volcanoes can produce sulfur. Methane can come from life, or from geological activity. Even oxygen isn't always proof of biology. It can come from broken up water molecules if a planet is bombarded with strong light. This is one of the biggest challenges in studying distant atmospheres, trying to understand what's normal for a planet and what might be strange. And the answers aren't always clear. Earth's own atmosphere has changed many times over its history. There were periods when it was full of methane, and others when it had almost no oxygen. If aliens had looked at our planet a billion years ago, they might not have seen any signs of life at all. If they had looked during the Industrial Revolution, they might have noticed a spike in carbon dioxide and thought something unusual was happening. Timing is everything. Future telescopes will be far more powerful than the ones we use today. Projects like the Extremely Large Telescope in Chile, or space-based missions still being planned, will be able to study exoplanet atmospheres in much greater detail. They could detect tiny traces of complex molecules. They might even be able to spot seasonal changes in a planet's air, like rising CO2 levels in the winter or falling levels in the summer. That kind of pattern would hint at biology. If the gases showed sharp jumps not linked to seasons or natural processes, it might point to technology. There's also the possibility of waste heat. Advanced civilizations use energy, and no matter how efficient they are, some of that energy will turn into heat. A whole planet warmed slightly by artificial means could stand out, or a planet with strange nighttime temperatures, too warm for its distance from the star, might suggest cities or factories releasing heat into the air. These are indirect signs, but they're still worth watching. Another idea is to look for light, not the light from the star, but light from the planet itself. Earth at night glows with electricity, from streetlights, buildings, vehicles. An alien planet might do the same. If we had a telescope sensitive enough to spot small flickers of artificial light on a dark hemisphere, it would be one of the clearest signs of civilization we could ever hope to find. But that's a dream for the future. Right now, we're still working on the basics. Even with the James Webb Telescope, it's not easy. Clouds can block signals. Atmospheres can be too thin or too thick. The distance makes everything more difficult. The more we understand about atmospheres, the better we become at reading them. That gives us a model. If we know what our atmosphere looks like during different periods of history, we can look for those same patterns elsewhere. How long would a city like New York last without humans? If all the people in New York City suddenly vanished, it might seem like the city would stay standing for a very long time. From a distance, the city looks almost unbreakable. But this is an illusion. Without humans around to take care of it, New York, and any modern city, would start to fall apart almost right away. The process would begin within days. One of the first things to fail would be the systems we don't usually think about: pumps, drains, and electricity. Cities depend on constant power to keep water out of places where it doesn't belong. New York, in particular, sits low near the coast. Without pumps running to push groundwater and rainwater out of tunnels and basements, the subway system would begin to flood. Some of it would fill up within days. The tunnels under the East River and the Hudson would soon be underwater. Once the power grid failed, and it would without workers to run it, lights would go out, heating and cooling systems would stop, and water pressure would drop. Buildings with internal plumbing would begin to fail as pipes froze in winter or burst from pressure changes. Wooden materials inside walls would begin to rot. Mold would grow quickly in the damp, dark spaces. Elevators would stop working, ventilation systems would shut down, and small fires, caused by short circuits or lightning, would burn unchecked because there would be no one to put them out. Outside, the roads would begin to crack. Plants are always looking for space to grow. Seeds blow in the wind or are dropped by birds. Weeds would find the smallest cracks in sidewalks and push through. Once they take hold, they grow quickly. Without people trimming, cutting, or pulling them out, plants would begin to reclaim the land. Trees would sprout between buildings and along highways. Vines would climb up skyscrapers, wrapping around windows and steel beams. Animals would return too. Raccoons, rats, and birds already live in the city. Without humans, their numbers would grow. Larger animals, deer, foxes, even coyotes, would move in from the surrounding countryside. In time, predators like wolves and bears might even find their way back. With traffic gone and the noise of people missing, the city would start to feel more like a forest than a metropolis. But the biggest changes would come from the weather. Wind, rain, snow, and ice are the great destroyers of man-made things. Over time, small damages add up. Roofs start to leak. Water gets into beams and supports. Freeze-thaw cycles cause expansion and contraction. A small crack becomes a big split. One wall gives way and the weight causes the floor above to collapse. Bit by bit, the buildings fall. In coastal areas, the threat from storms is even greater. Storm surges, hurricanes, and rising sea levels would all take a toll. Many of New York's tallest buildings are designed to sway with the wind, but they still rely on maintenance. Without inspections, loose parts could fall. Windows would break and never be replaced. Water would enter the interiors and pool. Eventually, corrosion would reach the steel skeletons. And then, decades or centuries later, even these towers could topple. How fast this happens depends on the materials and the location. Wood rots quickly, often in just a few years. Brick lasts longer but can crumble if the mortar fails. Steel is strong but vulnerable to rust. Concrete can survive for centuries in the right conditions, but not if it's exposed to salt water or constant moisture. Within 20 years, many residential buildings, especially smaller ones made of wood or mixed materials, would be falling apart or completely collapsed. Trees would be growing through the remains. Roads would be covered in dirt and moss. Nature would be everywhere. The outlines of city blocks might still be visible from above, but up close, it would look more like a forest or jungle. After 100 years, only the strongest and tallest buildings would remain. Some might still be standing, though hollowed out and crumbling. Steel beams would be orange with rust. Rooftop signs and antennas would have fallen. The subway system would be a network of flooded tunnels. Bridges, once carefully painted and maintained, would sag or collapse as metal supports failed. Without constant upkeep, even structures as massive as the George Washington Bridge could fail. After 500 years, it would be hard to tell a city was ever there at all. The forests would be thick. Soil would cover many of the roads. Rivers might change course, flooding low-lying neighborhoods and washing away debris. Animals would dig, burrow, and nest in old basements. Earthquakes, if any occurred, would knock down what was left. Fires might burn entire sections of the city and leave behind only ash and scorched stone. And after 1,000 years, only traces would remain. Some concrete foundations might still be found beneath the dirt. Metal objects buried underground, coins, stainless steel, or heavy machines might last longer depending on the soil. Plastics could still exist, though cracked and broken. A visitor walking through the area would likely see a wild landscape, not a human one. Without digging or testing, they might not know a city had ever stood there. Artifacts in orbit, a future Rosetta Stone? High above Earth floats a silent ring of machines. Thousands of satellites orbit our planet in layers, some still working, most long dead. Along with them are rocket parts, tools lost during spacewalks, old solar panels, insulation fragments, and even paint chips. To us, it's just space junk. But to someone, or something far in the future, these orbiting relics might be the most intact record of our existence. Space is cold and quiet. There's no oxygen to rust metal, no flowing water to wash things away, no tectonic plates to bury or melt the evidence, no plants growing over them or animals chewing them to pieces. And while space is not completely safe, micrometeoroids strike and solar radiation wears things down, decay happens much more slowly than it does on Earth. In the vacuum of space, Some things can last for thousands or even millions of years. In low Earth orbit, the situation is different. The upper edge of Earth's atmosphere still drags objects downward. Satellites in this region fall back over time and burn up in the atmosphere. But higher up, in geosynchronous orbit, around 36,000 kilometers above Earth, objects can remain for much longer. There's little to push or pull on them. A satellite placed there today could stay for tens of millions of years, spinning silently in a fixed position above the same part of the planet. It's this zone that some scientists and science fiction writers have imagined as a kind of time capsule. A satellite that no longer works might drift quietly for ages, untouched by erosion or decay. One day, if a future civilization on Earth rises again, they might rediscover spaceflight and find these objects still circling high above. They might tug a satellite down, open it up, and try to understand who made it, what it did, what it meant. And if they're careful enough, they might even find messages. Some spacecraft were built with the idea that someone far in the future, or even an alien civilization, might find them. The most famous examples are the Voyager spacecraft, launched in the 1970s. Each carries a gold-plated record with sounds and pictures from Earth, greetings in many languages, music, images of life, nature and technology, simple scientific data about where Earth is and what humans looked like. The records were built to last 1 billion years in space, though that depends on what they run into and where they go. Voyager 1 is now far beyond the edge of our solar system. If anything finds it, it won't be Earth-based. But closer to home, other objects might also survive. The lunar module descent stages, left behind by Apollo astronauts, still sit on the Moon. So do scientific instruments, flags, and rover tracks. While meteor strikes can damage the Moon's surface, objects there could last for millions of years. Future explorers, or archaeologists, might visit and find these things almost exactly as they were left. We've sent rovers, landers, and orbiters on Mars. Some crashed, some are still working, others are now silent, slowly gathering dust. Mars has winds and seasonal storms, but erosion happens slowly. A rover buried in Martian sand might be preserved for an extremely long time. It wouldn't rust quickly. Its structure might stay intact beneath the dust, protected from sunlight and radiation. And then there are objects in even more stable orbits. The James Webb Space Telescope orbits around a gravitational balance point called Lagrange 2 or L2. It won't fall to Earth, it won't burn up. Eventually it might drift or lose power, but its remains could circle the Sun for millions of years. Deep space probes that travel beyond the solar system could become drifting fossils of technology, untouched unless someone else finds them. What's remarkable is that many of these artifacts carry more than just their structure. They hold information, data etched into metal, memory chips, code, writing, symbols. Some of it is simple and obvious. Labels, instructions, identification plates. Some of it is complex and hard to read. Digital files, firmware, or command protocols. Future beings, if they're clever, might reverse engineer it. They might decode what the symbols mean. They might read the languages, trace the circuits, and understand how our machines worked. This possibility turns satellites into a kind of Rosetta Stone. The original Rosetta Stone, found in Egypt in 1799, had the same message written in 3 languages: Greek, Demotic, and Ancient Egyptian. It helped scholars crack the code of Egyptian hieroglyphs. Our space artifacts might serve the same role. If they contain repeated patterns, signals in multiple languages or formats, they might help a future intelligence figure out what we were saying, what we valued, how we saw the universe. Of course, this assumes the artifacts are found. Space is vast. Even geosynchronous orbit, though relatively stable, is huge. Satellites might drift, collide, or be pushed by small forces over millions of years. If Earth goes through major changes, like massive asteroid strikes or solar flares, it could take a long time before spaceflight returns, if ever. And even if it does, our old machines might be mistaken for natural objects, metallic rocks, tumbling shapes, simple debris. Still, the idea is compelling. If Earth forgets us, if the crust recycles all our cities and the oceans bury our traces, then space may remember. Our first steps beyond the planet might become our most lasting legacy. Long after books crumble and stone monuments collapse, a satellite might still spin in silence. It's not hard to imagine how a future civilization might treat such a discovery. They might treat it like we treat meteorites, rare, strange, and full of clues. They might study the materials and wonder how we made them. They might search for more, building catalogues of ancient space debris. They might launch missions to recover, clean, and analyze our earlier satellites. Our junk might become their treasure. And if we are not the first, if an earlier civilization once rose and fell long before us, then maybe we should be looking upward too. Perhaps, somewhere in a strange orbit, there is something that doesn't match, an object that doesn't belong, not made by us, but not shaped by nature either. If our machines can survive for millions of years in space, so could someone else's. How to leave a message across millions of years. Leaving a message that can survive for millions of years is one of the strangest and hardest problems humans have ever tried to solve. Most of the things we build aren't made to last even a few hundred years without repair. But what if we wanted to say something important? Something that needed to be remembered for 10,000 years? Or even a million? How do you talk to people who might live so far in the future that they don't speak your language, don't share your culture, and maybe aren't even human? This idea became more than just a thought experiment in the 20th century, when the problem of nuclear waste became real. Some nuclear materials remain dangerous for tens of thousands of years. If people in the far future stumble across a buried nuclear site, they could be harmed without ever realizing what they found. So governments and scientists began thinking about how to warn future generations, stay away. Do not dig here. One of the most famous efforts was a project in the United States called the Waste Isolation Pilot Plant, or WIPP. It's a deep underground storage site for radioactive waste located in the desert of New Mexico. The site is designed to hold its contents safely for at least 10,000 years. But even if the structure survives, how do you make sure no one digs into it in the far future? A group of researchers, engineers, artists, and historians came together to explore this challenge. They called it nuclear semiotics, the study of how to communicate a warning across deep time. They considered all kinds of ideas: giant stone monuments carved with symbols of danger, fields of sharp black stone spikes meant to look scary and unnatural, huge concrete blocks with messages in many languages, even biological markers, plants or bacteria that change color near radiation. One proposed design was called the menacing earthworks idea. It would surround the site with tall, uneven mounds and sharp angles, something that looks clearly artificial but also clearly unfriendly. Another concept used large granite slabs etched with warnings in different languages, along with pictures that might be understandable even without reading. These messages explained that the site contained something dangerous, not valuable, and should be left alone. But the people involved in these projects knew they were working in unknown territory. Languages change, civilizations fall, symbols lose their meaning. Consider this: if you found a strange message carved in an ancient script no one speaks anymore, maybe with a skull or a jagged line, would you stay away? Or would you become more curious and want to dig, hoping for treasure? Warnings don't always work. Some teams even explored the idea of creating myths, stories passed down through generations to warn people of the danger. Maybe a tale of a cursed place or forbidden land, something that survives through oral tradition, passed from parent to child. But myths change too. A warning might turn into a challenge. A place to avoid might become a legend about hidden power. Outside of nuclear waste, the same question comes up with deep time archives. Attempts to store information in a form that lasts for geological ages. Some researchers have tried carving messages into sapphire discs, sealed in protective containers. Others use metal plates etched with fine writing, built to survive heat, pressure, and corrosion. A project called Memory of Mankind stores clay tablets inside a salt mine in Austria, each one holding stories, documents, or cultural records in tiny lettering. There are also digital efforts. Some scientists have encoded information in DNA, since DNA can last thousands of years under the right conditions. Others have created special glass discs that can hold data using lasers, resistant to heat and damage. But all of these run into the same problem. Surviving physically is only half the battle. The other half is making sure the message can still be read and understood. Imagine a future archaeologist finding a small disk with millions of pages of text written in a dead language, stored in a digital format that no machine can read. It's like having the world's best library, but no key to unlock it. Without context, without explanation, without translation, the information is useless. This is why many deep-time communication projects focus not just on storing knowledge, but also on creating tools to help people in the future understand it. This might mean storing the same message in multiple languages, or using simple pictures, or creating primer texts that explain the basics of language and technology in case all of that is lost. One project aimed at leaving a long-lasting record beyond Earth is the Arch Mission Foundation. They launched a small archive into space, tucked inside a private spacecraft that orbited the Moon. The archive used thin nickel discs etched with tiny writing and images, something like a modern Rosetta Stone. The hope is that someone someday will find it and be able to decode its contents. Some thinkers have even imagined how to use geology itself as a storage system. What if you encoded a message into the layers of rock? Change the chemical composition of a stratum in a pattern that's clearly artificial. In theory, this kind of record might survive as part of the fossil record, but decoding it would be extremely difficult, and placing it precisely would take tools we don't have yet. Leaving a message for a future you will never see, to people you will never meet, about dangers they may not understand. It's a strange kind of legacy. It's not just about being remembered. It's about trying to protect others, or trying to tell them, we were here, and we tried to do the right thing. Most of us live in weeks, years, maybe decades. But these ideas stretch across millennia. They ask us to think like a geologist or an astronomer, measuring time in layers of rock, in orbits of planets, in slow shifts and long silences. They remind us how small and brief our time is, and yet how big our questions can be. Can we speak across deep time? Can we leave a message that matters? We don't know. But the attempt is part of what makes us human. The politics of an ancient predecessor. If someone were to discover solid evidence of an advanced prehistoric civilization, something truly global or technological from a time long before written history, would not stay confined to the world of science. It would be a story that spills across everything: education, culture, religion, politics, and even national pride. People everywhere would want to know what it means and where it leads. Governments would step in. Media would spread the news fast. Different groups would start to form their own stories around the facts, shaping what others believe. In many ways, the discovery would be as much about power and identity as it would be about history. The first question that would arise is about ownership. Who gets to make the official statements? Who has the right to study the remains or display any artifacts? If the discovery happens in one country, that nation might treat it as their property. But what if the civilization was spread across many places? What if it built something like satellites or left messages in orbit, something beyond modern borders? Suddenly, it wouldn't just be about the past, it would be about who controls the present. Nations might compete over who found it first. They might argue over where the evidence should be kept. In some cases, governments might even try to cover it up, either to keep it for themselves or because they're afraid of what it would mean for society. Even today, discoveries that challenge the accepted timeline of history often draw controversy. But this would be much bigger. It would shake the foundation of how we think about human progress and possibly about our place in the universe. Religious communities could have very different reactions. Some might embrace the discovery, seeing it as proof of cycles or divine plans that go beyond what is written. Others might see it as a threat to established beliefs. If a lost civilization used symbols or tools that seem familiar, people might claim a connection to it, seeing it as proof of their faith or their ancestors' greatness. Others might say it contradicts holy texts and treat it with suspicion or even hostility. Religious leaders would likely have to make public statements, guiding their followers through the implications. Meanwhile, cultural groups might start asking deeper questions. If this ancient civilization existed, who were they? Did they look like us? Did they speak? What kind of lives did they live? In some countries, people might see this discovery as a point of pride. In others, it might lead to fear or anger, especially if the story suggests that what we thought of as human might have once looked very different. Claims of ancestry, heritage, and legacy can turn into disputes between nations, tribes, or even political parties. People care deeply about where they come from. If a new civilization is added to the past, everyone will want to know how they connect to it, or if they were left out. Textbooks would need to change. Museums would have to update their exhibits. Teachers and professors would need to learn new material and explain it in ways that don't cause panic or confusion. How do you teach children that there may have been an advanced species on Earth long before modern humans? How do you present that idea without opening the door to wild conspiracy theories or misunderstandings? News outlets might report carefully, or they might lean toward headlines that spark emotion. Documentaries, social media posts, and opinion pieces would fill the space with different interpretations. Some would call it the discovery of the millennium. Others would try to discredit it. The flood of information and misinformation would be hard to control. Governments might try to take charge of the narrative, especially if the discovery has security implications. If the ancient civilization left behind working technology, power sources, or even blueprints for things we don't yet understand, military agencies would likely get involved. They'd want to control access, limit leaks, and study the material in secret. This could lead to conflict between transparency and control, between the public's right to know and the state's desire to protect. International organizations might step in as well. UNESCO or the United Nations could try to declare the find a global heritage site. Scientists from around the world would call for open collaboration, but cooperation would not be simple. Different countries would have different laws, agendas, and ideas about what should happen next. Some might want to preserve everything as is. Others might want to dig deeper. Still others might call for everything to be returned to the earth out of respect. And while all of that unfolds, there would be more personal reactions too. People would reflect on their lives. Some might feel excited, believing the discovery expands our understanding of what life and intelligence can be. Others might feel small or afraid. What does it mean if we're not the first? What does it say about the future of our own civilization? In schools and homes, people might start to rethink the long timeline of Earth, not just in terms of dinosaurs and ice ages, but in terms of forgotten knowledge. Writers and filmmakers would take inspiration, creating new stories about lost worlds and hidden pasts. Even the question of how the discovery is made public would matter. Is it announced through a press conference, a journal article, a leak? Would whistleblowers step forward with photos and data? Or would governments try to control the release, hoping to shape public opinion in their favor? The way the story breaks could shape everything that follows. In some cases, the discovery could bring people together, a shared moment of history that belongs to all humanity. In other cases, it might drive people apart, as different groups try to fit the new information into old beliefs. And underneath all of it is a simple, powerful idea. We thought we were the first. We thought we were the only ones. If we're not, then what else are we wrong about? What else is hidden beneath the layers of Earth, waiting to be found? Becoming a multiplanetary species, insurance against oblivion. When people talk about building cities on Mars or returning to the Moon, it can sound like a waste of resources. The technology is expensive, the timelines keep shifting, and the challenges, radiation, food, shelter, energy, are far from solved. But behind all the engineering talk is a deeper idea, one that isn't just about exploration or even survival in the short term. It's about insurance, not for a few decades, but for the rest of time. If everything we've built on Earth is swept away, by war, by nature, or by time, there's a chance that something of us could still live on, somewhere else. This is why some thinkers and scientists believe that becoming a multiplanetary species is not just a dream, it's a kind of backup, a way of spreading the risk. Right now, every living human depends on a single planet. We all breathe the same atmosphere, drink from the same water supply, and live under the same fragile climate. If anything goes wrong, an asteroid, a supervolcano, a sudden ice age, we have no second home. Earth could become unlivable and we would have nowhere else to go. History shows us how fast collapse can happen. Entire civilizations have vanished in just a few decades due to drought, disease, or invasion. The difference now is scale. With a world population in the billions, with global trade networks and shared resources, collapse today wouldn't just affect one region. It could affect everything. So even though Mars is cold and dry and full of problems, some see it as a place of hope. Not because it's better than Earth, but because it gives us another place to start again. Setting up a lasting human presence off Earth isn't easy. The Moon has no atmosphere and extreme temperature swings. Mars has dust storms, low gravity and thin air. The nearest stars are too far for now, but slow progress is being made. Space agencies have already landed rovers, tested habitats, and begun planning long-term missions. Private companies are launching reusable rockets and experimenting with growing food in controlled environments. The road is long, but the first steps have already been taken. Some people ask why we should bother. Earth still has beauty, life, and resources. Shouldn't we fix our problems here before running off to space? That's a fair point. Colonizing another planet won't solve climate change or inequality or war. But the two goals aren't at odds. In fact, they may help each other. The tools we develop for living in harsh space environments, clean energy, recycling systems, efficient shelters, could also help people living in difficult conditions on Earth. And the broader mindset that comes with space exploration, the one that looks at centuries instead of years, could shift how we think about progress. Beyond the practical side, there's also a psychological one. Knowing that we have a second home could change how we think about civilization itself. Right now, every book ever written, every piece of music, every language, every culture, everything is trapped on this single world. If something wipes us out, it all goes with us. But if even a small colony survives on another planet, the story doesn't end. Some of our knowledge, our memory, our questions would still be out there. It might not even take that many people. Some experts think that a few thousand humans, carefully selected and well supplied, could rebuild a thriving civilization. Even just storing our knowledge, books, videos, languages in off-world vaults could make a difference. These could be placed in underground shelters on the Moon, shielded from radiation, or floated in stable orbits around the Sun. They would act like time capsules, waiting to be discovered again. Of course, survival is only the first part. To truly make it, humans would have to learn how to live on these new worlds without constant support from Earth. That means mining local materials, growing food in soil or hydroponic systems, and making water from ice or chemical reactions. It means learning how to stay healthy without Earth's gravity, and how to raise families in low-pressure environments. These are not small tasks, but they are not impossible. As strange as it sounds, we may already be doing some of this work without knowing it. By sending probes to the outer planets, by mapping the Moon's surface, by designing smart robots that can fix things on their own, we're building the tools of independence. The next step may not be a giant leap, but a long, careful climb. And once that foothold is strong enough, we may find that we're no longer just Earthlings. We're citizens of more than one world. There's also a bigger idea at play here, one that goes beyond humans. If we plant the seeds of life beyond Earth, then even if our species fades, life itself may continue. It might evolve into something new, shaped by its new home. Just like life on Earth was shaped by rain, sunlight, and gravity, life on Mars or elsewhere could take a different path. In that sense, spreading to other planets isn't just about saving humanity. It's about keeping the flame of life burning no matter what happens here. Some have even imagined a future where Earth is just one chapter in a much longer story, where different planets host different versions of civilization, where each one carries a piece of the past and adds something new. In such a future, forgetting would be harder, because memories wouldn't be tied to a single place. They'd be shared across the stars. For now, that vision is still far away, but it begins with decisions we make today, about what we build, where we invest, how we think about time. If we choose to look ahead, not just to the next year, but the next 10,000, we may find that the idea of being a multiplanetary species is less about escape and more about responsibility. It's about taking care of the things we've made, our ideas, our mistakes, our dreams. Because no matter how clever our technology becomes, Earth is still vulnerable. It's still small. And as we've seen again and again, even the greatest cities can be swallowed. To avoid total amnesia, we may need to reach beyond the ground beneath our feet. Not to leave Earth behind, but to make sure it's never forgotten. Not because we're certain we'll fail, but because history shows us how easy it is to be erased. And because, in the end, the only way to outlast disaster may be to spread the story so wide that it cannot be lost all at once. So, what do you think about the likelihood of an ancient civilization existing tens or hundreds of millions of years ago? And if we are to meet their same fate one day, should we do everything in our power to become multiplanetary? Send us thoughts in the comments, and if you enjoyed the video, consider leaving a like and subscribing. Thanks for watching.